Thank you for being here. I just want to make some acknowledgement, and I skip the word to the host that we have here today, and then we will start with the scientific program of the conference. Okay? Welcome to the present edition of the IEEE CBMS conference, and I'm very honored that you are here today, so numerous, and I think that I'm sure that the conference will greatly improve with your contribution. Thank you. The CBMS attracts a worldwide audience and is one of the premier conference for computer-based medical system, and is one of the main conferences in the field of medical informatics and biomedical informatics. CBMS also allows researchers leading international projects and industries to share their experience and to lay the basis for future collaboration. I would like to take this opportunity to thank the steering committee of the CBMS for having supported the application of the current edition here in l'Aquila. And let me also acknowledge the colleague, General Chair, Alejandro and Rosa. We share some little piece of life in l'Aquila yesterday. And the program chair, Mayra, Joao and Jose, and the financial chair, Matteo, who called me at in the late night to check the final, and all the local chair. They are too much, and I cannot mention by name. A special thank goes to the publicity chair that thanks to their and their huge effort we have had, we reached a very huge number, about 250 submission, and it is a very, very important number that demonstrates the validity of and the vitality of the CBMS community. Then I want to extend my personal acknowledgement also to the institutional and the industry partner that in various forms, as you can see, greatly contributed to this event. And in particular, a local institution, the University of l'Aquila, that hosts the conference, the Gran Sasso Science Institute and the city of l'Aquila are all here represented by distinguished colleagues, to whom I am very happy to leave the floor. So I thank you very much, and we can start with their greetings. Thank you. So, if you agree, I can give the word to the Deputy Rector of the University of l'Aquila, Professor Fabio Graziosi, for the intervention. Thank you.
So, good morning to all of you. I'm Fabio Graziosi, I'm a professor in telecommunications, and I'm here today on behalf of the Rector of the University of l'Aquila, Professor Edoardo Alesse, to welcome you to our university and to our city, hosting for the next 3 days the IEEE 36th International Symposium on Computer-Based Medical Systems. Thank you for coming. So medical informatics and biomedical informatics in a wide sense are the research and application areas characterizing this symposium. In this context, the research community moved and is still moving from a frustrating pioneering period in which almost all the technologies needed in the chain to support real-world applications seemed to be mature, but some of them quite systematically failed, thus spreading the feeling of unfeasibility and unreliability to all the applications. So the research community is moving from this frustrating pioneering period to a more consolidated stage where all technological ingredients appear to be finally ready to support real-world applications today. So this evolution mainly derives from a shift of the scientific community towards a decidedly multidisciplinary approach to research and technology transfer, breaking the outdated boundaries between scientific sectors and promoting cross-fertilization. So this approach, as far as I know, definitely represents the leitmotif of this symposium from the very beginning of its story. So the University of L'Aquila too considers the open-minded multidisciplinary approach as one of the strategic guidelines for its future development. So we are very interested and honored to host a symposium as this one, and I would like to thank IEEE for choosing L'Aquila for the 36th edition of CBMS. A special thanks also goes to local organizers of our university who have been working hard for many months to ensure that every organizational detail was addressed at the best. Well, once again, welcome to the IEEE International Symposium on Computer-Based Medical Systems, and I hope you will have a pleasant stay in our city for these days. Thank you.
Now I introduce you Professor Paola Inverardi, who is actually director of Gran Sasso Science Institute, past rector of the University of L'Aquila, and also one of the colleagues that will present as a keynote speaker here. Thank you.
Thank you. Too many hats, too many roles, but it's a great pleasure for me to be here and welcome you and join all the other welcomes that you are going to listen at. And I will not say too much because tomorrow you will be exposed to my talk, and I might be a little bit more concrete in what I will discuss about the symposium and my personal research. One thing I would like to tell you is what is Gran Sasso Science Institute. It's a new institution. You all know that L'Aquila was struck by a devastating earthquake 14 years ago. And after the quake, there was a great effort of all the community, including the university. And one of the output of the effort that the government put in the reconstruction of L'Aquila is actually the Gran Sasso Science Institute. So it was a very initial project, very ambitious. I mean, just after the quake, L'Aquila was destroyed. There was originally this very big university. We had over 20,000 students. After the quake, we had 0 building available, nothing. And the quake was in April. In May, it started this effort pushed by the government to understand which kind of strategic project could have been useful to help L'Aquila in redeveloping the economical structure of the city. And the top project that was selected in July, after research of the OECD, was the initial idea of the Gran Sasso Science Institute, which, if you think of it now, I mean, looking backward, imagining that the first project that OECD thought in terms of redevelopment of the territory in July, when there was nothing here, and even the university was struggling to resist and to exist, was to build another school, a PhD school. I mean, it's very ambitious, very visionary, but as a matter of fact, this was done. Today, Gran Sasso Science Institute is one of the high schools in Italy. It's actually extremely very well positioned in terms of research, and it's contributing to the educational research ecosystem of L'Aquila, which is University of L'Aquila that obviously redeveloped, Gran Sasso Science Institute, and the National Institute of Nuclear Physics that has a very famous lab very close to this place. And this makes the system very strong. And after 14 years, we can say that betting on knowledge, betting on education, betting on higher education was a very successful bet. So I think that for all of us that work in the scientific field, it's, it's something that we have to think of it and remember. We undervalue our contribution in terms of the development, economical and social of a territory. No? And, education and research is knowledge-based. Basically, I mean, it's knowledge. It's the people. And then when you have the people, then you have a lot and you can actually try to have ambitious goals. So this is also my end of welcome and it's my encouragement to a conference, and that will be very successful and very active, I think, and I hope. And I also hope that you will enjoy being here. I mean, you will still see some of the effect of the quake, but you will also see a lot of the rest. So thank you very much and have a nice day.
Now I invite the Dr. Ercilia Lancia, the Counselor for Tourism, International Relations and Promotion of the City of L'Aquila. And please.
Good morning, everyone, and welcome to L'Aquila. I bring the institutional greetings of the Mayor, Pierluigi Biondi, and of the whole municipal administration, but also my very personal one, that I am Councillor of Tourism. I want to thank you for choosing this city, my city. But maybe L'Aquila is easy to choose. L'Aquila is a city of a character, and I hope you can visit it in this day. I want to thank you for your work, because the science work is always a work of all humanity and for all humanity, always. I want to thank you for this conference here today. It helps to increase what is called the quality of life of a city. Have you thought about it? I do because I administer this city. But above all, thank you for this debate. I know it will be of quality. I'm sure of it. First of all, I can say this because I trust scientists, and then because I already know, looking you in the eyes, that you will remain human, always human in a digital world. So I thank you very much, and have a good work.
Last, I want to invite here Professor Guido Macchiarelli, the Director of the Department of Life, Health and Environmental Science of the University of L'Aquila. Thank you.
Thank you, Professor Clashidi. Ladies and gentlemen, distinguished speaker, it's a real pleasure for me to be here and to welcome all of you in this beautiful city and in this important university. I can tell you my department is the Department of Medicine, but not only, because we have environmental science and biological sciences. This means that we look to the life and we look to the human being as a whole. And so, in this moment, I think that this meeting is really appropriate for our goals. Our goals is the human being in a good environmental and in a good fashion. So it means that we need the help of computer-based medical system. This is not the future, it's the present. I tell you that today without medical system we cannot work, and we appreciate very much the work of all informatics and people that are helping us for preserving human health. Today we can have remote diagnosis, we can have remote surgery, we can have intelligence, artificial intelligence that help today us every day for working better with our patients. And our patients can have a further hope in the future because of your work. So for us, I think it's really important to have all of you here. It's really important to see many young people that for us are the future. It's really important for us to enjoy the efforts of Giuseppe Placidi, that I thank particularly because he's one of the most protagonists of our department. We believe in him and we know that he can give us a future project on informatics and computer-based medical systems. So thank you for being here again, and I'm sure that this meeting will be really successful. Thank you.
Thank you to the host, and thank you very much for the intervention. Thanks. And now I leave the floor to Alejandro, who is the General Chair, colleague, and CBMS, and also member of the steering committee. Please, Alejandro.
Hi all. Well, it's a pleasure to be here, especially because the last edition of the CBMS that was in person was 4 years ago. Because of the COVID, we have been online in China, online in USA, and online in Portugal. So it's a real pleasure to be here. Probably you don't know me. I hold the chair of the steering committee of the CBMS, and I have to say that this year have been really difficult because organizing a conference where you have this uncertainty about if will be success or no, because you don't know if will be finally be able to be done or not, it's really difficult. And this year was even more difficult because it was expected to be the first year after Cordoba in 2019 that we were able to be in person. And I was discussing a lot with Rosa and Giuseppe, especially about how the things will go. And I have to not only thank them, but congratulate them for their work, because this edition has been, as far as I know, probably the one that most submissions has received. I don't know if all the editions, but by sure, in the last 10 editions, I'm quite sure that this is the fact. And I think that this is part of a very good job that they did. Also, program committee chairs, financial chairs, so I want to thank all the people that has been involved in CBMS, but especially I want to thank you, because at the end, CBMS is the people that came here, is the attendees, is the people that submit their papers, the people that will share their knowledge here, and the CBMS and the community that we have is because of you. So from my side, nothing else. Thank you very much for being here, and I give the floor to Rosa that will explain the program. Thank you.
Good morning to everyone. So now the real information on what awaits you in these 3 days. So are you curious? I hope so a lot. Okay, so just a few information about, as said Alejandro, how many submissions we had this year. We had 238 submissions. So a huge success. So thank you to all of you, because it's also your contribution that makes CBMS, and mainly your contribution actually. And also thanks to all the reviewers, because we involved more than 300 reviewers for helping us in this job. And we had submission of, from 51 countries, so many of them. And this is a huge achievement to see how CBMS is going worldwide. Now, a few tips about the program. So since we had a lot of submissions, we have a lot of sessions. So we have 40 sessions this year. And mainly we organize them with a thematic division. So the main track has different themes. So each session you will see in the program there's a little title at the beginning, an acronym that identifies which topic. So you can choose whatever you like to, whatever suits you or raises your interest. And we have two special tracks. One is AI for medical imaging, and the other is data-driven and hybrid solution for human in the loop. And you'll see that these are also, there are also dedicated sessions of these two special tracks, and probably more than one session for each one of them. And finally, last but not least, we have the project in the industry track, where you will see the contributions of industries and people that are working on European projects. So please take a look at this too, because it's very interesting, and also what is the impact, the practical impact of the research we do. Then delving a little bit into the program more, we have 5 parallel rooms. So the Aula Magna, that is this room, is one of the 5. And in this room that we are in now, there will be all the keynotes and also the closing ceremony. All the other sessions are distributed, you will see in the program where, so the room is specified. And we have more or less one particular track beside the main track each day. So for example, the first day we have one special track, the second the project and the industry, and the last the other special track. Also, some important things. Today is the longest day of sessions. Tomorrow and the day after would be a little bit lighter. And in the afternoon tomorrow, we have the social activities and social dinner. So I will delve into that a little bit more later. About the start of each day, we have distinguished speakers, and we have one per day. So after the opening ceremony, we will start with the first keynote speaker that will be introduced later on. So these are the three distinguished speakers that accepted our invitation, and we are very, very proud of their contribution. And we will see later on. I don't spoil you about the names and their and what we will talk about. About the social activities, we will have a city tour from 3 to 7 p.m. and you can have the QR code to find more information. The start of the city tour is the fountain that you probably saw coming here. And then we will go through all the city and see some ancient buildings, the Spanish castle and Mammoth and so on, with 2 beautiful churches. And it will end, we will get a look also to the 99 fountains. I suggest you may want to use comfortable shoes. It's not a very long walk, actually. It's just the time that it takes to see all the different things. But it's best if you make comfortable. About the social dinner, we have the social dinner tomorrow at 8:30 at this beautiful location, and which is the Magione Papale. And there is no dress code needed. We will have passes for the transfer from the surroundings here. The meeting point is La Villa. You will see tomorrow after the guided tour where exactly the buses will pick you up. And the meeting point is a little bit earlier. It's at about 8:15 in the PM, and we will go there together. There are no tickets that you will need. You will need to bring your own badge probably, so if there is any change in this information, we will provide you that. About the communications, how we will communicate these days, besides the email, but something that is faster, I think, is using Slack. So we provided a workspace, and you can access the workspace by accessing the link. And also, you will find the proceedings at this link. We sent to all of us a preview, but you can still access them if you didn't receive the email with this link here and the username and password. Finally, I would like, as all the colleagues said, but it's very important to thank all the people that contributed to the organization, and special thanks to the program chairs that together with us general chair did a lot of work, and also to the finance chair, Matteo. And unfortunately, she's not here, to Bridget, which is our publication chair, which did very much. She did a great contribution to the organization. So enjoy now. It's time to start.
We're going to start with the first keynote that will be given by Professor Harald Smith. Harald is professor and the head of the Department of Pharmacology and Personalized Medicine in the University of Maastricht. He was the coordinator of the H2020 Repo Trial project, and he is currently the coordinator of the Repo for EU project. I know Harald for a while, and I saw many of his talks, and I think that you will enjoy it a lot. So Harald, when you want, the floor is yours. Thank you.
Can you switch this on? Do I have to switch it on? Nobody's there. Can you switch this on? The yellow one? Okay, I usually like to run around. Okay, so is my medical colleague still here who gave this welcome? No. Okay, anyway, so what we are doing is really to make sure that the potential of bioinformatics really ends up with patient benefit. And there are a couple of issues along that road. Okay. On the other hand, it's not a trivial thing, just another research area that we are working on. You may have heard of the contractive waves. The contractive waves were the major socio-economic revolutions in our society. They have usually a cycle of 40 years. And they really change everything. And sort of, one was the invention of the steam engine that basically induced the industrialization and everything associated with it, the good things and the bad things. But it was a reaction to a crisis. There was a deep need for a new energy source in the British mining industry. That stimulated the research on another engine or another energy source. Also, the invention of an electric light bulb was not an incremental improvement of a candle. It was something completely new. And you will agree that the most recent contractive wave that we had was the IT revolution. Changed everything. But we are at the end of the IT revolution. And the question is, what do we do with it? And a lot of futurologists agree that the next big thing is not renewable energy. You know, that's just another energy source which is known for decades. Politicians were just too slow to implement it. And also Industry 4.0 is not a real innovation. It's just digitalizing standard workflows, make them a little bit more efficient. It's not a conceptual change. The next big thing is a complete redefinition of cycles define health, how we preserve health, and how we cure diseases. And mind you, all these ways start with a crisis. Now you might think, crisis, what crisis? We have a pretty good healthcare system. So I take the first part of my talk that we don't have a perfect healthcare system. So one talk, hello, can you switch it on? Can you ask him to switch on this microphone? I can switch it on. Oh, you can switch it on. I pushed this one a couple of times. Oh.
Super, many thanks. So, one problem that we have in medicine is we basically do not understand any disease. What usually happens is that a patient out of a state of total well-being maybe comes with a symptom to a doctor, or the patient thinks he's completely healthy and the doctor measures the blood pressure is too high, or the cholesterol is too high, or blood sugar is too high, or some blood cells look a little bit weird and so forth. And what then happens, the disease is named after that symptom. So, hypertension, diabetes, whatever. But there is no molecular understanding what causes that symptom. So, and as a result of that, the only thing we can do is to treat the symptom. It's like if your car is broken, the headlights constantly burn out, and then you bring your car to the garage, and the garage boss says, well, I know what your problem is. Your headlights constantly burn out. You say, I know that, but why? Well, I don't know. You have to now, every 3 months, come to the garage and we put in new headlights. Well, you would not accept this. You would then go to a different garage that maybe finds out why this is happening. But in medicine, no doctor can tell you. The only thing is they can treat symptoms. And that's why we have so many chronic diseases. If you can't repair something, it becomes chronically defect. So the term chronic diseases, by definition, is a capitulation of medicine. No accuse of medical doctors. They do their best, but the knowledge is just not there. So 70% of what a medical doctor does is actually prescribing a drug. And these are the 10 drugs with the highest turnover, but it's the same for any other drug in 2015. And the green patients are those who will actually benefit from those drugs. The red patients are those who will also receive the drug, but we know they will not benefit from them. We call this the number needed to treat. We know this for every drug, for every indication. How many patients do I need to treat with a drug so that one patient has a benefit? You can look it up, it's not a conspiracy theory, you can look it up in any phase 3 clinical trial. There's a website, thennt.com, you can look it up for any drug in any disease. We have to treat all 25 here so that we reach this one. We cannot differentiate between the green and the red. We have to treat all of them. And the red ones, if they're unlucky, they will experience the side effects of the drugs. So they're actually worse off. They would have been better off if they were not treated. What about new drugs? The pharmaceutical industry has experienced an exponential cost explosion in the 90s. It costs now, it stabilizes at a value of about $2 to $3 billion to bring one drug successfully to the market. Of course, this one drug has to counterfinance all unsuccessful developments of this company. That's how this value is calculated. But despite this gigantic increase in costs, the new medical entities that have made it to the market, that green line, is more or less constant. So if in an industry the costs explode and the output stays the same, I think you will all appreciate this industry has a slight problem. And interestingly, it's not a recent problem. Since the 1950s, the number of new drugs per billion US dollar is constantly declining. And actually, that's a logarithmic scale. And it has not been due that tighter regulations were introduced in the 70s. You may remember the thalidomide scandal when there were much more requirements to bring a new drug to the market. And also the new biologicals that some people think they are wonder drugs. They have the same attrition rate like all other drugs. Actually, this is called Eroom's law. It's the reverse of Moore's law, which I'm sure you are familiar with, where sort of you were able to print more and more transistors on chips per area. Actually, drug development is getting worse and worse and worse. So obviously, there is a conceptual problem, how we define diseases, and then after that, how we develop drugs. And one consequence of that is that the pharmaceutical industry has almost retracted from all indication areas. There are some areas where for 30, 40 years, there has been no innovation at all. And this shows all indications in medicine. The size of the bar, sort of the new drugs that were introduced to the market, and red means the most recent ones. And so you will see there's not a lot of red on this figure, actually only down here. And if we zoom in, there are only 3 areas where actually some innovation is happening. That's antiviral drugs, immunomodulators, also in cancer therapy, and anti-cancer agents. It's quite easy to bring an anti-cancer drug to the market. I mean, if you increase the life expectancy for 2 or 3 months, you can bring a drug to the market. So it's a gray zone, I would say, in evidence-based medicine. That's it. Everywhere else, pharma is retracting. They're now moving to gene therapy, actually, a lot, because there you have really a monogenetic disease, a clear disease definition, and a relatively safe development. So, what are the reasons for this? Usually we claim, also in our research grants, we need basic research, obviously. Then, if we want to translate it for medicine, we need preclinical research, which is usually animal experiments. Then comes clinical proof of concept, and as an end result, you have patient benefit. If we're really, really honest about this, this sequence is completely broken. Basically, basic scientists and preclinical scientists are mainly busy in producing publications, preferably in high-impact journals, with which you get more funding. And what do we do with this funding? We produce more publications. Every one of us is in this hamster wheel. No one measures whether out of your research, maybe after 10, 15 years, eventually some patient benefit has emerged. I mean, I don't expect it from a junior scientist, but from a more senior scientist who has spent money for 10 or 15 years, I would occasionally ask, and you are working in medicine, any improvement for patients achieved? No, but I have a publication list of 250 papers. Super. Patients will love it. And of course, we have quality problems. You know, of course, this whole reproducibility crisis. I mean, you all work with data, but you also should be aware that 60% of the biomedical literature is not reproducible. 60%. And of course, there is the sample size issue. If you have very low sample size, you can always detect also in genetics wonderful effect sizes. But if you really increase the effect size, very often nothing remains. But if you want to publish quick, you do a bit less samples and have significant values. That's also the holy grail, the p-values in research. It's an interesting study that looked at the p-values for secondary outcomes that were also measured and for primary outcomes of a study, so which were relevant whether you can publish the paper. Secondary outcomes shows a fairly expectable p-value distribution. Primary outcomes, oops. There is a little peak just below 0.05, and then afterwards there is a dip. You know, it's obvious what's happening. They call it p-value hunting. And even if the p-value is significant, very often the study was not even powered statistically to measure the p-value. So we had a big issue where also one of the diseases we're working in is ischemic stroke. Ischemic stroke is not treatable in the moment. You can only take out the blood clot or dissolve it. After that, there's no treatment. And we had some targets validated, some targets we rejected, but there were 8 papers out there which said, no, this is a target in stroke. We said, not in our hands. And then basically all these other papers were not even powered to measure what they called significance. There was no randomization, there was no blinding of the investigators, so obviously a huge bias was introduced. Quality is very difficult to measure in science, but there is one measure in protein crystallography where you have a really precise measure. Is it a good crystal structure or is it a rather iffy crystal structure? And this paper analyzed in all journals where such structures are typically published. How is the quality? So a negative number is a bit counterintuitive, is a good crystal structure. A positive number is a rather bad crystal structure. Now let's have a look where the bad crystal structures are published. Nature, Cell, Science. Cell and Science, the worst crystal structure. So these journals don't even have the highest quality data. They have the sexiest titles maybe, but not necessarily the highest quality data. But the biggest problem that we have done in medicine is that we have divided up the human body organ by organ by organ. For every organ, we have a clinician, a neurologist, a clinic, neurology, and a research discipline, neuroscience. We have a cardiology department, the cardiologist, and cardiovascular research, and so forth. So even research works in this silo. So we think if we only look at the heart, whatever we see there is our disease, we define it, and if the patient has any other symptom in any other organ, we refer them to another specialist, another research discipline. I'm not interested in this. I'm only working on the brain or on the heart and so forth. The rest is irrelevant for me, by definition. Or another very nice disease definition is name a disease after a doctor who first observed it. So Alzheimer, Parkinson, super disease definitions. Now to the positive side of things. The big thing is now digitalization. But if we digitalize everything that we currently do and leave everything else, the rest, we will achieve nothing. Digitalization is not the answer. It's a small tool, it's a small component. But we need a total paradigm shift in medicine. So from a candle to an electric light bulb, basically. For me, the eureka moment was this paper. Probably many of you know him, Laszlo Barabashi. He's a physicist, actually. He is a network scientist. He works on all kinds of networks, social networks, airplane networks, spices for cooking, really all kinds of networks. And in this paper, he did the network of all human diseases. Something a human brain could never do to look at the same time. It's just too much. There is a good reason why medical doctors have sort of specialized. It's just not doable for a human brain to have the entire medical knowledge in your head and up to date. You know, it's just not possible. The human brain needed to somehow split it up. And here he looked at the entire network of all human disease. The color code is according to how we currently split up disease in our mainly organ-based or symptom-based ontologies. And the edges in between are in this case, the shared risk genes. So this gene, for instance, is a risk gene in 3 diseases, and it induces a link between them. And if you look at all diseases and all risk genes at the same time, you get this network. And in these networks, you see there are clusters forming. And the clusters form because these diseases obviously share a lot of common risk genes. And most of these clusters are multicolored. And that means diseases that we separate in different clinics, that we work in different research disciplines, actually belong together. And as long as we insist on separating them, we will never resolve them. That's absolutely essential. And what we are doing now is actually not so unusual. We just turn the whole thing around. A bit like in rare diseases. I said it before, they're very often monogenetic, so the molecular cause is totally clear. And even those patients have very often symptoms in 2, 3, 4, or sometimes 5 organs. One gene is affected, and still you have symptoms in several organs. So basically, if we flip this around, then what we currently call diseases are just the symptoms, and the genes that link them, they are a way to find the underlying causal mechanisms. Of course, there are diseases there which are umbrella terms, like hypertension might have 10 different mechanisms. Parkinson, we know, has probably 14 different molecular mechanisms. It's just a description of a symptom, but it's in principle the way we do it, and this is when we started to change our research completely and also to work intensively with a lot of bioinformaticians. Alejandro, Jan Baumbach, Jörg Menche in Vienna, Emil Güne, Joe Loscalzo. So it's quite a large group. And of course, you can look at it also in 3D. It should start, but it didn't. Oh, it does. The 2D representation is, of course, an approximation. The bioinformaticians always tell me, yeah, we don't need 3D, you know, it doesn't change the data, but for a medical person, it makes a lot of, it's very attractive to visualize things. So that's always a discussion I had with Jan Baumbach. So for us, it matters because you can put on VR glasses, and then you go to your favorite disease, you look for the genes around, or you go for your gene of interest, you look for the disease phenotypes around. It's cool. And so we work basically on this cluster here, which is on first sight a little bit weird mix of diseases. So that diabetes is in there, stroke is in there, heart failure, but also asthma, Alzheimer, dementia. So a weird mix of diseases, but they are linked through common genes. and risk genes. But we're also not only our genes and sometimes the genetic data for a disease may be a little bit iffy. So you can generate these networks also in different ways, namely, for instance, by shared symptoms. So if two diseases share a lot of symptoms, they may actually be the same disease. Or comorbidity, if two diseases very often occur in the same patient, maybe it's the same disease. So none of these networks is really perfect in the moment, but if you triangulate between them, and we have the NetRex platform in RepoTrial developed for them, totally open access, you can then extrapolate from each other. And we're not the only ones, we're not ghost drivers. There's, for instance, Christina Kiel, who's now in Padua. She worked on these retinopathies up here, clinically, histologically, one disease, but she showed it's actually mechanistically 3 entirely different diseases that just look the same. And this is a paper from Ellinghaus, where they looked at immune diseases and in this way linked them to drugs that are effective in more than one immune disease and thereby networked them. And there have been, even in medical journals like Lancet, papers who said, let's not call asthma anymore, or rheumatoid arthritis. These are really completely outdated disease terms. We should not even use them. We need to subtype or endotype this and also look at the comorbidities. And then there was a nice paper from Sanchez Vega on basically looking at all cancers, and they claimed they can explain all cancers by 10 cancer pathways. More complex cancers have several pathways affected, less complex cancers, only a few. I will come back to that. So I show you an example for hypertension, heart failure, and stroke. That's what we clinically work on. In this cluster of diseases, we found a couple of genes that were related to cyclic GMP signaling and to, let's say, reactive oxygen species formation. Some people call it oxidative stress, but that's a nonsense term. So, and there's actually evidence from preclinical literature that there may actually be unwanted interactions between those pathways if they are dysregulated. So it made kind of sense. We looked into that. Now, what geneticists now do when they have genes, and that's sort of the paradigm shift to you from us, they annotate these genes to KEC pathways. KEC pathways are man-made mind maps. People write up everything I've ever heard about tyrosine kinase signaling, everything I've ever heard about calcium signaling, cyclic AMP, and so forth. These KEC pathways have nothing to do with reality. These proteins exist, but these pathways in this form do not exist. I know it's almost a reflex in bioinformatics, but KEC pathways are useless. It would not have helped us to annotate the genes that we have to altogether 400 proteins. What shall I do with it? You know, I mean, it's pointless. It's not leading anywhere. I know you can publish it, but it's not leading anywhere. So there was a very cool paper this year in Nature from the Allen Institute. They actually stained every structural protein, not signaling protein, structural protein in the cells. I think they did millions of these stainings. Then they integrated them all. And what they basically showed in a nutshell is we assumed a little bit like all the organelles in the cell, they are randomly distributed and so forth. But what they actually showed that all the different organelles, they basically concentrate in certain areas, forming almost organs within a cell. And the important thing is, within these domains, you see that there are little subdomains formed. So little modules connected to module, connected to module. And that's how it looks. And you may also know the watercolor pictures from Goodsell, where he integrated what we know from structural biology, microscopy, and bioinformatics. This is how a cell looks inside in reality. What you often find in nature, there's this receptor, there's a second messenger formed, it swims over there to a kinase, something is phosphorylated, it moves up to the membrane. There is not the space in the cell for that. The cell is packed with proteins. The protein concentration in a cell is 300 milligram per ml. You cannot generate this protein concentration in a cell. It's basically protein only, and then a few water molecules inserted here and there. So you have to change how you think how a cell is organized. Yeah? There is no space. Yeah? It's densely packed, and this module concept makes a lot of sense. Yeah? You cannot have the entire tyrosine kinase pathway with 400 proteins starting from here, and then right is the cyclic AMP pathway, and left is a calcium pathway. That's just not how the cell works. So what we then, and there's another paper from Manuela Zaccalo from Cambridge. She has worked on cyclic AMP signaling assayed by phosphorylation. So finally, via a kinase, you get a couple of proteins phosphorylated through cyclic AMP signaling. But what she showed is she gets, I think it was 16 different phosphorylation modules. It's always cyclic AMP that's signaling. But it's doing different things in different part of the cell. So there is not the cyclic AMP pathway. It just does not exist. Delete KEC pathways. Delete. So how can we then come to a signaling pathway that we can then target and to a disease mechanism? So we started with the interactome. Basically all validated protein-protein interactions in the cell. The interactome has a lot of issues, I know. Every protein appears only once. Nonsense. From the 16 phosphorylation sites we know, a kinase must appear 16 times in different locations of the cell with different partners. Okay, thereby the interactome generates by definition hubs. Yeah? Basically, if you go to a kinase, all proteins that have ever been phosphorylated by a kinase you will find in the interactome all around a kinase. So these are shortcomings, but there are ways around it. So what we did in this study is we looked in the interactome, took as seed genes the cyclic GMP and reactive oxygen related signaling proteins, and then we look, can we observe a protein-protein interaction module where both come together, the green guys and the red guys. And there was only one module that's really distinct with first neighbors found. And here the green guys were related to the NOX5 gene. Out of all these 300 ROS-related proteins, one seems to be relevant. Of course, there are gazillion methods to construct these protein-protein interaction modules. So, and there was also a paper on that tested all of them. So we used two other methods. And interestingly, in all three cases, NOX5 was the key protein that apparently interacted. So of these two KEC pathways, only this part and this part are relevant. The rest may be relevant in other diseases, but not in this disease module. So the NOX5 gene, interestingly, is not present in mice. So it was preclinically not studied. So we did a knock-in mouse. So we knocked in the human NOX5 gene with a promoter that mimics roughly the expression pattern in humans. And the mice were hypertensive. quite severely. And remember, hypertension was one phenotype in our disease cluster. So that's somehow matched. And also the mechanism matched, not going into detail, it interfered with cyclic GMP signaling. And then we went into patients and looked, can we use just the NOX5 protein to identify patients that have this disease mechanism, so where this signaling module is dysregulated. And this shows the expression of NOX5 in normotensive patients, and most hypertensive patients have also more or less normal levels of this NOX5 protein. But there is a clear subgroup of patients that have elevated NOX5 levels, and that's exactly in line with the sort of hypothesis that you have an enzyme upregulated. It produces too much reactive oxygen species and then interferes with cyclic GMP signaling. So in those patients. And also that's important, a lot of people do omics and measure biomarkers and so forth. We think only those biomarkers are relevant that have a bimodal distribution, not normal here and disease over there. In biology, you have always only subtle shifts, yeah? But definitely a bimodal distribution. What we do usually in medicine, you know, blood pressure is perfectly normally distributed in the population. Cholesterol level is perfectly normally distributed in the population. And then we arbitrarily say, okay, from here on, we call it disease, and this is healthy. That's arbitrary. If you have a bimodal distribution for a biomarker, that's a little bit more convincing, I would say. And heart failure, as you remember, is also a phenotype in this disease cluster. And there is a form of heart failure which actually affects 50% of all patients with heart failure. And the current heart failure drugs do not work in those patients. So they are not treatable. 50% of all heart failure patients. And indeed here we see maybe in a 1-to-4 ratio also a subgroup of patients. And of course we treat only those patients with drugs that normalize this disease module. Those patients have to be treated with other drugs. There we have to find other mechanisms. They just share a symptom, but they have a different disease mechanism. And how we come to this treatments, we're not now starting a drug discovery process. In these two projects, we combine bioinformatics and systems medicine with drug repurposing. I'll show you why this is so successful. So RepuTrial was, we're not in a soccer match here. RepuTrial was the starting project, and now we're building the Repu4U platform. It's not just a project, but we built a totally open European-wide platform. Actually, we're going globally already in the moment. Everyone can associate with it. Everyone can collaborate it, and we will convert it into a permanent European infrastructure, because the EU is totally convinced about this organ-agnostic approach, and they're totally convinced that the era of drug discovery is over, and what we now need to do is drug repurposing. And I'll show you why. I mean, of course, it's one obvious advantage is that you can skip basically 12 years of development of finding a compound. You can directly go into a clinical trial. And I show you one example here. I mentioned we're also working on stroke. Here again, we have this module, this cyclic GMP signaling, then this reactive oxygen species signaling, and then you can have this upregulation of NOX5 in hypoxia, actually also NOX4, and then some nasty chemistry happens in between those two pathways. You don't need to understand what exactly is going on there, but as an end result, this signaling is basically kept, and up here a lot of toxic radicals all of a sudden are overproduced with a lot of unpleasant chemistry behind them, so not good. Yeah. So what you want to do, you want to reinitiate this cyclic GMP signaling and somehow stop this overproduction of radicals here. Actually, we call this network pharmacology. That's another thing that is also done wrong in the moment. We often try to explain a disease by a single target and want to cure a disease with one drug. That's not going to work. Except for rare diseases, which are really monogenetic. Most other diseases will be these small signaling modules, and a little signaling network is better treated with 2 or 3 drugs targeting several points, and with this you could correct it. The problem was, however, there is no NOx inhibitor on the market, and there is no NOS enosyntase inhibitor on the market. So we had no drug to repurpose. And now comes another paradigm shift. So if you think a beta blocker only binds to beta receptors, that's naive. So in this paper, they have modeled over 400 drugs to the then known protein structures. And you have indeed a few compounds which bind only to 1 or 2 proteins. But you also have a couple of compounds on the market that bind to hundreds of proteins. Same binding site, same affinity, not in millimolar concentration or so, same binding site, same affinity. And this area in cheminformatics, and basically in average, a small molecule on the market binds to 32 other proteins in average. And this field in cheminformatics, it's called the pocketome. So they looked actually how many different pockets can proteins form. I mean, for a small molecule to bind, you need a deeper or a shallow, ionic, hydrophobic. You need some pocket where the compound can fairly specifically or with high affinity bind to. And apparently what they find is that the number of different pockets is small. It's between 1,400 or 2,000. It's not totally clear yet, which means we cannot develop more than, let's say, 1,400 or 2,000 different drugs. That's it. With those drugs, we will have covered all possible binding pockets in all proteins. And maybe we don't need all binding pockets. That's why we think the era of drug discovery will soon be over. Why should we eternally need to discover new drugs? There must be a time when we say, okay, we've got all the drugs we need. So for us, the consequence was that we actually found that an anti-thyroid drug for a completely different indication, totally different target, is an extremely potent inhibitor of brain enosyntase. And an antipsychotic, totally different indication, totally different targets, perfect inhibitor of this NADPH oxidase. And we're now doing the clinical trial with this triple combination. The nice thing about this is because in such a network, you generate, of course, a lot of synergy. When we now combine drugs, we have maybe 5 or 10% additive effects because most drugs only act on symptoms. But if 3 drugs target the same mechanism, they are very, very synergistic, so you can lower the dose of each drug even to a level that the drug on its own would have no effect anymore. But if you give these super low doses, you get the full therapeutic effect, which also means all the other targets that each of the drugs target somewhere else will probably not be reached because the dose of the individual drug is so low. And then this way, we hope we can normalize the situation. Now to this cancer paper from Sanchez Vega. I mean, what we think and really eventually found out, the mistake they made is this reflex to associate the gene variants they found to these 10 cancer pathways, and here are the different tumors they looked at, and these are these 10 KEC pathways. They think with those they can explain all cancer. But if you start looking actually deep into it, how the signaling really works, they are totally connected. So in the end, it's a hairball again. So these KEK pathways are not the answer, also not in cancer. So we have now therefore also entered cancer, and we work with the lowest hanging fruit, so low complexity cancers, for instance glioblastoma in children or thyroid tumor. These are lower complexity tumors. We don't want to start with the hardest nuts like colon cancer or lung cancer, which are too complex. Let's test the principle in these cancers. Well then, to really make sure we have all genes and we have it quantitatively, we did a systematic review and a meta-analysis of all the papers that have ever been published in the not so frequent thyroid cancer. And there we have another problem of these genetic studies. If we took all studies together, there were over 18,000 genes, and we have only 22,000, to be associated with thyroid cancer. Well, that can't be. So, of course, there's an endless stream of single occurrences, but obviously there are statistics issues with a lot of these papers. So what we then do, we use the ELBO algorithm to at one point say, okay, up to here, we consider them as seeds, but not further. You know, that's too rare. And from those, we construct then, in this case, all possible modules that can occur in thyroid cancer. We don't expect that there is such an unfortunate patient where really all these modules are affected. Of course, we need to convert these modules then also in proper signaling pathways. Just the protein-protein interaction network does not teach us what actually is going wrong there, but that's sort of expert knowledge. So what we then do in a preclinical trial, we select the drugs for each of these modules. We rank them also for potential side effects. Then we do cell pilots from cancer patients to validate that detecting those modules and treating them actually works at a cellular level where the readout is maybe growth or replication. We don't want to kill cells. It's an innovative therapy in cancer, not with cytotoxic agents where you hope that the cancer dies a little bit earlier than the patient. It's normal drugs. We are dealing with signaling pathways, so we should be able to treat cancer with normal signaling drugs. And then in the clinical trial, the 2A trial, we do ethics by design. We are in close contact with regulators, and we basically do 10 N-of-1 trials, because in each individual patient there will be only a certain set of modules affected, and therefore each patient will get only those drugs related to his or her modules. And that's then basically the trial design. So in summary, we think research needs to change completely. We don't want to treat mice or rats, and we also don't want to generate only nice paper in Nature Genetics with some nice colorful graphs, but no medical application. So there are so many data out there. I was really surprised, if you really look for it, how many useful data you can apply. Of course, one needs to do multi-omics because none of the single data sets is sufficient. Eventually, we need to probably also consider the microbiome or the microbiome metabolites rather. Internet of Things, because behavior is a huge point. I didn't have the time to talk about. 80% of all disease risks we will be able to keep down with lifestyle intervention. We don't need to drug every sort of person who has a genetic disease risk. 80% we will be able to control with that, but the problem prevention is also in the moment imprecise. Everything is suggested to everyone. You know, everyone should eat healthy, sleep well, don't smoke, don't drink, reduce stress, walk 10,000 steps per day, and so forth. And that's just too much for everyone. So if we can tell someone, okay, out of this whole checklist, this number one thing, maybe don't eat red meat because you really have a colon cancer risk, top. Really don't eat red meat, yeah? Or keep it low, yeah? Then they can properly adhere to it. And so we need completely different disease definitions, a molecular pathology. It makes no sense to do genetics on diseases like hypertension or asthma. It just makes no sense. And we can probably translate it pretty fast through drug repurposing. I showed you why. What we actually then work on most in the moment is we can't do multi-omics for 20,000 euros on every patient. We have to, once we have identified a genetic risk, we then need to develop very affordable, cheap, simple tests that even a GP can do to monitor, is this specific risk in a patient manifesting or not? A bit like the tests for NOx5 that I showed you. This can be easily converted into a lateral flow test, which you all know from Corona. Whether we actually need animal research anymore, I mean, I've done it for 20 years. I'm very skeptical. Maybe there are a few cases left, but if an animal has a certain symptom that is similar to a human symptom, but how do we know that the mechanism why this symptom occurs in this animal is the same as the mechanism why the patient has the symptom? So, and if we don't know this and we know the patient mechanism, why not go to a clinical trial right away? So in the end, we will only have 4 disease types in principle. We have the rare diseases, we have those oligogenetic diseases with a huge lifestyle component. Cancer is not so much different. You have inherited and acquired mutations, but you still have a signaling network that you can treat. And even infectious diseases are not so different. Here you have the infectious agent, let's say the virus. The virus needs host proteins that generates a network. You treat the network, both virus proteins, but also host proteins. In principle, it's always the same approach, network pharmacology. And with this, we should be able to eventually cure diseases, so repair the light machine, not constantly exchange the light bulbs. Or, if that's proven a couple of times, that we're really confident about the disease risks, why not treat it at a time point where we detect, oh, some biomarkers indicate that the disease risk is manifesting. Let's start treatment already now, so that the patient will actually never experience his or her disease symptoms. So, in summary, the consequences of that is we have to end organ-based medicine. We have to start systems medicine. This is only doable with the support of AI, decision algorithms. It's the end of big pharma. We will soon have all the drugs that we need. It's also the end of single targets. It's the end of pathways. Get familiar with these signaling modules or nanodomains, as cell biologists call them. And with this, we will then have precision diagnosis, precision medicine, and precision prevention eventually. This is the Repo4You platform project. Please join us. You can write to us. We would like to associate. We would like know more about it, we're doing next conference is in Stockholm at Karolinska, 25th, 26th October. Very interdisciplinary. We don't have separate sessions. We have everything together because it's very important that also bioinformaticians discuss with medical people or clinical trialists and vice versa. Also in medical research, we must not work in silos. We really have to understand the other disciplines and discuss with them because the innovation never happens within a discipline. It always happens between disciplines. And that's it. Thank you.
Harald, is there any question for Harald?
Yeah.
So,
the boss, no?
might I use the second one? Yeah. Imaging is a super area where AI works. That's sort of the...
Thanks. Right, so it's interesting you say that because I didn't hear much about radiomics, about imaging of the, let's say, evidence of a disease, but perhaps when you said symptoms, there you include as well biomarkers. I'm not sure, in fact, because you spoke about cause, about shifting towards multi-omics data where the cause of a disease can be perhaps found and explained for better therapy, more target drugs. And just to give you the example, because it's all I know, it's about multiple sclerosis. So actually for us in imaging the lesion, the evidence of multiple sclerosis, we can find the answer to more accurate treatment for the patient, so what you may call personalized medicine. And all in all, what I want to say is that perhaps it's not all about multi-omics, but multi-omics plus other types of data, such as linking multi-omics with radiomics, here included MRI.
Any data,
yeah, just because I felt maybe there was not space in your talk for that. And so if we think about using artificial intelligence method, I suppose that one key objective is integration of those type of data as well with multi-omic data such as genomics and so on.
Yeah,
what do you think about that? Okay.
Yeah, of course, imaging data can also be useful, but we just experienced in Alzheimer's disease. Alzheimer's disease can be wonderfully imaged with amyloid. There have been wonderful amyloid-lowering drugs, none of them effective. Disaster. So, and I would also say multiple sclerosis is not really a treatable disease. You can treat it, but it's not a curable disease. It's probably also several diseases. You can definitely achieve something for patients, but we are still far away from curing it. So, but I agree, imaging data can definitely be part of the multi-omics process. I think it's too early for artificial intelligence. What we are doing are the first clinical trials that try to show to use a mechanism-based disease definition for an effective therapy in a disease subtype. We have to do this a couple of times so that AI can learn from some of our positive examples, then predict another set of positive examples that we had, and then maybe start predicting the next ones. It's just too early. In the moment, you cannot use AI for drug discovery because you basically use it on flawed disease terms, on flawed signaling pathways. It just cannot work. It can't work, AI at the moment. AI needs to have a set of working examples from which it learns and from which it predicts. We don't have these yet. In rare diseases we have it, but in rare diseases you don't need AI. You know what the problem is. So it's really too early.
Okay, yeah, just I thought maybe the focus in the near future would be maybe to integrate all the available data towards...
Yeah, sure, that's what we do in this Networks platform. It's multi-omics, everything we have is integrated in there, including imaging, but imaging is also basically describing a symptom, maybe measuring a specific marker. It's measuring, describing a symptom, it's like a blood parameter and so forth. It's not it could be one element to do triangulation between diseases and come to a molecular cause, but we have to come to a molecular cause. Imaging cannot provide to you the molecular cause of a disease.
No, I didn't mean that. Just I meant maybe we should aim to link the two.
And we do it. It's done.
Great.
Yeah, in multi-omics.
Thanks.
Yeah.
Okay.
My question is short. Thank you very much for the talk. I was wondering. Thank you very much for the talk. I was wondering about the data. You have been mentioning data about the bases are from genes. Now, this is an expensive procedure to acquire them, and in several cases, it does not agree with the diagnostic procedure. If somebody is treated for tinnitus, asking the person to give gene information is a little different than for some other diseases. So have you considered biases in the samples that you have?
Yeah. So we are very selective in which patient cohorts we go. So we work, for instance, with Estonia in the moment. They have a totally unbiased cross-sectional biobank and gene bank. So we work with them. UK Biobank make work, BBMRI might work, but we are, for instance, very careful when a clinician has collected 500 samples in its lifetime and wants to build his entire career on giving out these samples. There may have been a huge bias. It's only from one center and so forth, definitely. You have to be very careful on which samples you look.
And because of the publications that you have mentioned, it might be that some of the publications with the 18,000 genes are...
Yeah, or they did not correct for multiple testing properly, could also be.
I think it was, in fact, at one of the CBMS conferences some years ago, where somebody gave a talk on herbal remedies and the informatics of herbal remedies. And it seemed to me at that point that the Eastern herbal remedies people believe you can't be normal unless you're taking a herb. Right? My question is about the future. At what age are you going to start testing people because they're asymptomatic? And how many drugs are you going to allow them to be on while you counter things that you can't see?
Well, first of all, I think genetic testing will become a routine thing in the future. On a Black Friday, you can get, I think, whole exome sequencing for 160 euros. That's 40 euros more than these Corona PCR tests cost, or what labs charged for it. And I mean, taking multiple drugs, it's not unusual. I think 40% of 40-year-olds, 50-year-olds, and 60% of 60-year-olds take 10 or more drugs every day. And they are not effective. So I think if to start a drug therapy when the non-pharmacological prevention has failed, only then, needs, of course, before then, the evidence that this signaling defect will 100% lead to this disease phenotype in 10 or 20 years. You need to generate this evidence first before you can consider doing a drug therapy as a preventive measure. That will have certain ethics issue, but in the long run, I think it is foreseeable.
Thank you. I'm not an expert, and thank you for your talk, but you talk about precision medicine. What about personalized medicine?
Yeah,
and, what is the space inside this?
That's an allergic term for medical doctors, because the medical doctors rightfully say, with the current tools and the current knowledge we have, we try to do for every patient in front of us the best possible solution, so personalized. So they would probably say, we are doing personalized medicine in the moment, but they can't do precision medicine, because these precise diagnostics and these precise disease definitions and precise therapies are not there. So with systems medicine, we can move, or we can enable these doctors who want to do personalized therapy so that they can actually start doing precision therapy. Thank you.
Okay, so, well, I think that we are a little bit out of time, so we are going to conclude. I would like to thank Harald again for being our keynote. And Harald, we have a gift. We have a gift for you for being the keynote. Thank you very much. So you can reach Harald maybe at the coffee break. So,
Yeah,
well,
I'll be here all day.
good. So we will start now with the parallel sessions. Thank you very much.
So, Alejandro, shall we be starting, or is there a... Yeah. Yeah. Okay. So, hi everybody. Let's relax and start. I'm Iris Piliapoulou from the University of Magdeburg. I'm chairing the first session of the day. And we have 3 talks. We are a smaller session, so we can go a little bit relaxed. On that, you have 15 minutes presentation, and then we have up to 5 minutes for the discussion. I hope it will be a bit more quiet. And I would like, we have the first 2 talks are from the same team of Alan Tucker. He's the last author in the Brunel University in the UK. And the first talk is on privacy assessment of synthetic patient data, and Ferdows is presenting. I will start the counter as soon as you start, so you have time.
Good morning, everyone. I'm Ferdows, and I'm going to talk about privacy assessment of synthetic patient data. To be exact, how to quantitatively assess privacy preserving of synthetic data. Basically, in this paper, we quantify the privacy gain of synthetic patient data extracted drawn from 2 generative models, MSD and PrivBase. And these 2 models are tested using real primary care data extracted from CPRD UK Clinical Practice Research Data Link. But before that, we need to mention that privacy-preserving data analysis and re-identification attacks were a matter of discussion since 2000. Back then, several approaches, traditional approaches were introduced to address, such as k-anonymization, to address re-identification attacks, but it was proved in many cases that k-anonymization is not sufficient for addressing the re-identification attack. It's not enough, and especially in the case of high-dimensional data, and that brings us. And that brings us to the synthetic data, where synthetic data comes as a remedy to protect privacy. So basically, we want an anonymization mechanism that takes raw data that contains some sensitive information and generate a synthesized version of this data that has 3 properties: utility, fidelity, and privacy. So utility refers to the fact that the data should be fit for the purpose of defined use case and for the accuracy of specific inferences from the synthetic data. And fidelity refers to the fact that the data should be a good representative of the reality. That is, the synthetic data should capture the distribution of the real data. And privacy refers to the fact that the synthetic data should not leak any sensitive information about the ground truth data, and in case of disclosures, this privacy preserving should be evaluated. So, basically, we want, on one hand, the synthetic data retains the utility for statistical analysis, and on the other hand, prevent it from the adversaries. So this is not a trivial task because there is a tension between preserving information for statistical analysis and at the same time hiding it from the adversaries. So this is so-called privacy utility trade-off, and we want this trade-off to be maximal by getting the high privacy and utility at the same time. So how to measure privacy? There are two approaches to measure privacy. One is differential privacy, and one is adversarial approaches. So differential privacy is built on the concept of randomized response in statistical methods to collect sensitive information. This randomization techniques enables plausible deniability, and these techniques ensure that any responses to the query, regardless of being included as a responder, can essentially equally likely to occur. And this parameter, this concept actually represented as a parameter epsilon, and the smaller is the epsilon, the better is the privacy. Although this technique is robust against attacks, but it is very hard to apply it to any particular data analysis because it's hard to train an algorithm that has the differential privacy property and still be useful for the statistical analysis. And it's hard to communicate this mathematical concept with the stakeholder, the concept of epsilon and data. So that brings us to the second approach, adversarial approach, where in the context of the synthetic data, the adversary who actually study the code of generative model for the synthetic data tries to infer some sensitive information from the original data set and wants to check the vulnerabilities. This can be membership inference attacks where, say, you have a target, say Firdaus, and you want to see whether my target is a part of a training data set, whether I am in the original data set or not. Or it can be inference, attribute inference attacks. So you say you have some records, say gender, zip code, and age, and you want to infer my salary from the synthetic data. These concepts are easy to communicate, and also it's easy to apply meaningful analysis, and it covers a diverse range of attacks, but there is a lower bound of the risk. So to give you an idea about the membership inference attacks, so consider synthetic data was published to the public, and this synthetic data was generated on the patient who was diagnosed with HIV positive. Then the adversaries who has access to some old patient data, and this synthetic data, which is published to the public, runs inference attacks, say membership inference attacks, and learns those particular patients were in the records on which the synthetic data was generated. So this is a disclosure to the privacy. So recently, a toolbox for adversarial approaches, adversarial privacy auditing of synthetic data were introduced and developed, called TABAS. And about the perspective of this toolbox, can say that it covers a diverse range of data set, currently only tabular data, but It aims to cover time series data and networks data, and it covers a wide range of threat models, and it can deploy any synthetic data generated models, open source, but still under development. But how does this toolbox works? As an input, you just give it a real data and generative model, and the main thing you have to do is to design your threat model. By threat model, I mean what the adversary knows about the attack. This can be specified in three things: knowledge of synthetic data generative models, knowledge of data, and goal of the attacks. And then you can apply several attacks based on the literature and checking the vulnerabilities. And the output is a report on the quantitative evaluation of the attack success over the generative model and real data. So in this paper, for the data set, as I said earlier, we used the real anonymized primary care patient data, which is extracted from CPRD. And this data is focused more on the clinical characteristics of the patient who were diagnosed with COVID or suspected to the COVID or COVID positive. And for the generator, we focus on two generator, MSD and PRIV-based. And how we design the threat model. In this paper, we focus on the black box knowledge. By black box knowledge, mean the adversary knows the generative models for the synthetic data, and it can apply that function on any arbitrary data set. And for the knowledge of data set, we apply two approaches. Auxiliary knowledge and exact knowledge. By exact knowledge, we mean that the adversary knows the data set is either D or D dash, where D and D dash differ only in one particular record. And for the auxiliary knowledge, we only consider a random sampling of the large population. And the goal of the attack, for the goal of the attack, we verify two cases, both attribute inference attacks and also membership inference attacks. And we applied several attacks like close distance, and random queries, shadow modelings, and we checked the vulnerabilities. So for our experience, we wanted, for our target data set, we wanted to see the vulnerability of the synthetics data on both outliers and also random records. So from the outlier analysis, I have chosen two particular records, and by random sampling, two records were chosen, and differential private parameters based on the standard choices were chosen, and the raw data from the raw data, the synthetic data was generated using the model MSD and PRIV-based. And for the threat model, as I said earlier, we focused on the black box knowledge. And for the auxiliary knowledge, I give access to the adversary of the 50% of the data, and we implement several attacks, and the threat models were evaluated. And for each attacks, we have a report that considers the accuracy to true positive rate, false positive rate, and privacy gain. These are the results when the attribute inference attacks were implemented at the generator via MSD. As you can see in some, you can see we have a drop when we have a random query in the privacy gain. This is the result with the attribute inference attacks where the generator is prive-based. And this is the result when we have a membership inference attacks and the generator is MSC. And as you can see here, we have a drop, especially in the drop in the privacy, especially when we have an outlier target. but in case of private base, you see when we implement the membership inference attacks, the privacy gains is still around 1. Is more robust in comparison to the MSC generative model. So I choose a target, outlier target, and I studied the ROC curves of this target when we have access to, we have implemented the membership inference attacks, and about the knowledge of data set is exact knowledge. As you can see, in terms of private base, the ROC curves are near to the random classifier line, just like flipping a coin, and this is good. This means that the private base is actually robust in this case, but when we implement the MSC generator, we can see that the area under the curves cover more and the accuracy went high. So here I have to mention by accuracy we mean the success rate of the attacks, and the lower is the accuracy, the better is the privacy gain. If we want the privacy of the individual to be preserved, the ROC curves should be near to the random classifier, like flipping a coin, and if it is outperform and it is far from the random classifier, means the privacy gains is less. So, although synthetic patient data achieve high privacy in most of the attacks scenario, it doesn't behave uniformly against adversaries, and we saw that the vulnerability of the synthetic patient data varied depending on the threat models and algorithm used for generating synthetic patient data. And we showed that the private-based generator is more robust generator in comparison to MSC. And at the end, we have to aim to find a method and mechanism to ensure the privacy gain of almost 1, regardless of the attack scenarios, type of generator, and threat models. You can ask questions.
Thank you very much. And also for keeping time, questions? I will start with the evaluation. If you go back to the true positive, false positive rate, exactly this one, I was wondering whether how is it wanted that we are close? Is it wanted that we are close to the random queries?
Yes, yes. So, yeah, so we have some measures for the report. One is accuracy. Accuracy here defined as a success rate of attacks. So, and this is based on the false positive rate and true positive rate. So we don't want the accuracy of the attacks to become very high. So when it is near to the random classifier means the accuracy is low. It's like flipping a coin. It's 50% there or 50% is not there. Suppose my record in the training set. So, but when suppose for the shadow modeling and random queries, the area under the case reached to the 64%. That is the accuracy of that is more. That can identify whether my record was a part of the data or not. So the true positive rate were high. So in that case, we see that the privacy is not preserved even we have a synthetic data for the outlier.
I think the idea of the attack, of using an attack is very good. I am wondering how would this work if we have a classifier that actually sees the labels? What would be the performance of this classifier?
It
would be up there, right?
I didn't
I have a classifier that sees the labels. So the only thing it sees is the labels.
Okay.
And then it adds some noise into it. What would be its performance then?
Performance of the RC.
Yeah. Would it be up there?
This classifier doesn't have noise. The noise is injected in the generated model.
Yeah.
So we don't inject any noise there. We inject the noise based on the Gaussian in MST and based on Laplacian method in preface. So we don't put any noise here. That in terms, but I'm not quite sure about that. What do you mean by
what I mean is how much of what I see is due to the classifier quality, how much is to the quality of the model, and how...
It depends to all of them. It depends to all of them. Yeah. In case of noise, when the injection of the noise is less, like using it's not that much robust, and again you can see that the vulnerability of the synthetic data goes high. But when it's more robust, like private with the injection of the noise, you can see it's close to the random classifier. But in those cases, it's like you are checking. In case of membership attacks, you have a record, and you want to see whether that record was a part of the generating data set or not.
Yeah.
So you have only that things about the, I don't know how...
Yeah, it does.
Yeah.
Further questions? Yeah. Let's give the right.
I can say, how do you handle with the, when we have privacy, we have lots of information, right?
Yes, utility privacy.
You need to select if you want to a lot of details or if you want to give privacy. How do you compare this with the techniques that are there, like anonymity, LUCT, and the other ones that you presented? I know that when we applied them, we lost a lot of records because of the algorithms. Did you check that, or did you feel that you lost information, or the percentage of records that you lost were significant?
Okay. In this paper, I didn't verify the utility, but after that, for my study, I studied the utility. But like in case of NHS in UK, they have their own version of generating a synthetic data, and in that they define the utility based on their user's case. So mostly in the industry, I see they define it based on the use case of how they preserve the utility and how much they want that privacy to be preserved. So case to case can be different.
Other questions? Okay, this is not the case. Thank you very much. We come to the next speaker. Same group this time. We are again on synthetic data, but now these are geospatial patient data, and we might present.
Hi everyone, this is Dima Al-Attar, and today I will walk you through our paper, and as its name suggests, is about creating synthetic geospatial patient data while preserving privacy. Synthetic data in healthcare refers to artificially created data that is created to mimic real patient data while maintaining their privacy by not including any personal information about them. Usually, the synthetic patient data includes risk factors and demographics and information about those patients, but it doesn't include any sensitive data types such as their physical locations. The problem with associating synthetic patients with physical location is that real patients, excuse me, real patients can be inferred from this data. Therefore, to protect patients' privacy, there is not much data sets published to public for use. However, as it's known that people's health is highly influenced by the environment in which they live and therefore by their geographic locations. And having access to spatial synthetic patient data can have a lot of benefits. For example, we can identify the people at risk. We used always to think that people at risk are the old people. But what if the people who are at risk are the younger people who live in more polluted areas or the people who live in rural or urban areas? Therefore, it's important to understand the context of people's health, and spatial data can be great in creating these contexts. It also can be helpful in identifying the gaps in healthcare resources in some geographic areas and how can we fulfill it. And the most important thing, it will be very important in understanding how the diseases are spread between people and why different geographic areas are affected by certain disease more than others. And we can consider it as a starting point to study machine learning models spatially. In our framework for data synthesis, we need two types of data sets. The first one is a population data set that includes information about sample of individuals. And the other data set, it should have some statistics about the first data sets. To build our model, we used a study case. In this study case, we used the COVID-19 symptoms synthetic data set from the CBRD database as our population data set. This data set includes synthetic patients with risk factors and demographics information, and whether these patients have been diagnosed with COVID-19 or not. This data set was built based on real health records for primary care patients in the UK. For statistics dataset, we used the quality and outcomes framework from the NHS database, which has some statistics about the general practices in England. For those who don't know, general practices, or GPs, are the main healthcare providers in England, and they are distributed through all England. This dataset includes the number of people who are registered in each GP and the prevalence or percentage of people who suffer from different health conditions. So our main aim is to use the quality and outcomes framework statistics to allocate the synthetic patients in the CBRD data to the GPs. And by that, we will give the patients a physical location that is similar to the location where they were allocated. And why we are doing this is because we know as a fact that people in England are registered with the nearest GP to their home or work. And therefore, by registering them with their GPs, with the GP, we will give them a location that is similar to the place where they usually spend their time. So to do that, we have to assume a base population for England, which was 5 million people. And we will use the regional distribution of population from the quality and outcomes framework as our base distribution. By multiplying these together, we can find the population size in each region in England. Using the regional population size in each region and the same approach, we got to more local areas inside England until we reach to the boroughs, cities, and then the GPs. And for each GP, then we find a new list size or a new people counts based on the 5 million population that we assumed. Using the new list size, we then find using the new list size and the prevalence of diseases, we find the counts of people who suffer from each disease in each GB. Now, for the second step is to allocate the synthetic patients from CBRD data to the general practices that we created. For that, we will take each GB separately, and we will select the patients who have the same deprivation score as that GB. Then we will reorder the risk factors in each GB, in the GB from the rarest condition to the most common one. And starting from the rarest condition, we will take a sample size from the CBRD patients that has this risk factor with a sample size similar to the required size in that GB. And we exclude the other patient with that condition. Then we will consider the other risk factors in the sample that we chose, and we will use this for the next sampling rounds. We repeat this for each risk factor and each health condition until we reach the list size that we need for that GB. We repeated the same steps for around 7,000 GB inside England, and until we reached 5 million population. Now, to evaluate our results, we need to make sure that both data sets, the statistics and the population data sets, has maintained their underlying distribution and characteristics. First, we started with the statistics data set, which is the quality and outcomes framework GB. For that, we conducted a correlation test between the risk factors in the simulated GB profile, and we compared this to the correlation results from the real GB profile. And in our results, we found that the simulated GB profile has captured the same weak and strong relationships as the real GB profile, and there were no significant differences between them. And to evaluate if the real population from CBRD data has maintained its characteristics in the simulated allocation data, we built a random forest model to predict the COVID-19 diagnosis inside England. The random forest model was trained on data from all England, and it was tested regionally. We built two models. The first one was trained on the allocation data, and the second one was trained on the real data from the CBRD. Then we compared the accuracy of the two models. The results showed that the allocation results performance was almost similar to the gold standard, and in some regions, such as Greater London and Northwest, it outperformed. Finally, we wanted to check if the real location of the patients from CBRD data can be inferred in the simulated data. To do that, we evaluated where the people who were allocated to a certain region are originally coming from in the CBRD data. And in our results, we found that except for Greater London and East Midland and Northwest, the patients were allocated to a region that is different than their original region, which can even increase the privacy of the CBRD data even more. To conclude, in our approach, we tried to maintain the patient's privacy by using synthetic data in our simulation instead of using real-world patient data. And we used general statistics about those patients instead of using personal information about them. We know this approach is simple, but we had a good results from it, and it can be extended to other populations as long as we have some spatial statistics about them. But we have to make sure that the population, to choose the right population size to mimic the statistics correctly, otherwise we would have different results. And we can consider this kind of data a starting point to study the machine learning models spatially, and it would be a great way to study the diseases, characteristics, and to put individuals' health in the context of their environment. Thank you.
Gender, age, and location, right? So the disease conditions, like.
Yeah. So the GB profile have the distribution of people who are registered in GB. By that, we will get the spatial distribution of diseases. Okay, and using the common variables or the mutual variables between the GB profile, the distribution of diseases in each general practice, with the same conditions that we have in the CBRD data. We only sample instead of taking the distribution, because we already transformed the GB profile from statistics to counts. So instead of looking at the distribution, we are now dealing with counts. CBRD, it's not open source, you have to... Okay, so the GB profile dataset is an open source data. You can find it on the NHS database website. But the other dataset, the population dataset, it's a closed source dataset, and you have to apply for it on the CBRD website. Yeah. You have to apply to get an access for it. Yeah.
Questions? I have a joint question to this one. You said the GB profile data set is public. So after the anonymization, after the synthesization, let's say, did you check whether the GB profiles are the same as before?
Yeah, as I said here, that in the simulated data, I transformed the data again to get a similar GB profile, and then I did correlation tests between the variables in each GB profile and compared if the correlation results are the same. So yeah, I did it.
Yeah. The question goes a little farther than that.
Yeah.
If they are not the same, then there is some sort of an indication that there has been an anonymization that affects a synthesization that affects the reality, let's say, in a publicly visible way.
So if the synthesis was not successful?
Well, if the synthesis was very successful, and so successful that, as you said, some people were assigned to a GP that was in another region.
Yeah.
Now this implies that the profile of the original GP has changed.
Well, you can't say it's changed. We are just taking the people who have similar health conditions and that can be allocated to different areas. For example, in London, we can have people that have the same diseases that we have in East Midlands, for example, right?
In that case, there will be no change essentially because the fictive patient, the synthetic patient is moved from GPA to GPB and vice versa, and we see no difference. However, how are we sure that there is no difference, not in the correlations, but in the GP profile itself?
Okay, so I tested how the GP profiles changed in other ways, and the profiles were the same. Now the problem that we have is that we only take one risk factor at a time. And by that, we may be changing the GP profile because we don't have enough data to study when people have multiple diseases. So by that, you are right, but it's just because I don't have enough data to simulate this. Yeah.
Further questions? No further questions? So thank you very much.
Thank you.
The last talk by Ericsson, we are moving to Brazil and to stay, of course, with the privacy, but now we are more on the security side, and we hear about vulnerabilities in explainable models.
Hi everyone, my name is Ericsson. I am a PhD candidate at the Università of São Paulo. Today I will present the paper Assessing Vulnerabilities of the Deep Learning Explainability in Medical Images Analysis under Adversarial Settings. And medical images have been widely applied in help to identify diseases. The physicians using the medical images to identify. For example, in COVID-19 pandemic, medical image was an important asset to identify COVID cases. And the deep learning also an important set of techniques to assist in decision making. And however, these methods, such as deep learning, are black box methods, hard to understand your behavior. So, explainability methods are proposed to improve the transparency of these methods. In the last years, the deep learning have advanced. So the deep learning has improved the accuracy in classifying medical images. And methods such as the GradCan has proposed to explain the behaviors of the deep learning. However, one issue in this context are security issues. However, these methods may be compromised by adversarial attacks. And our main concern in our proposal is the deep learning security to classify medical images. One example of attack is adversarial attacks. Adversarial attacks inducing the misclassifications of the model, of the deep learning model, for example. Some examples of these attacks are the fast gradient signal method, FGSM, and the projected gradient descent. Let's observe this image, this figure about one attack. We have one clean image, this clean image combined with a noise level, for example, 0.4, multiplied by a noise of this. This noise is generated by one function defined, for example, for the fast gradient signal method, and resulting in a adversarial example or a perturbed example. Past studies in literature usually training one model and test this model to improve the accuracy or robustness of the model in classification process. Other papers in literature propose these layers, for example, adding the FGSM and PGD attack to generate adversarial examples. One issue in these attacks are weak attacks. These attacks can be identified by adversarial training, for example. And these attacks is based on gradient. One issue in these papers did not verify the attack behavior and lack of the methods to analyze the attacks. For example, the methods to analyze the behavior using the GradCam. Our proposal, we add this attack, the deep full attack. One optimization attack is a powerful attack compared to FGSM and the PGD. And we evaluate the attacks on the GradCam, evaluate the influence of attack in the GradCam. And we analyze the read maps of these images, these perturbed images. Our proposal this is the workflow, our proposal. And the step one, our proposal. First, we selected the chest X-ray images in scenario one, this scenario one for binary classification. And in the scenario two, using the OCT image, optical coherence tomography images, and for mood classifications. And in the next steps, we normalize these images and balance the class for classification. And the second step is the process of the training the algorithm, the models. We split the data set into test and training, and we select the well-known models to classify medical images, such as the ResNet, the VGG, and the Inception, and apply the fine-tuning process to improve the accuracy in these models. And the second step, the third step, is apply these attacks. To apply these attacks, and we execute the FGSM, the PGD, and the deep full attacks in the test phase of these models, and generate these perturbed images, and next to the evaluation process. In the evaluation process, we analyze first the training and test metrics of the classification, the training test methods of the classifications, and for clean images. And the second analysis is the vulnerability analysis. For vulnerability analysis, we evaluate the visual analysis, analyze the influence of the GradCam, the attacks of the GradCam in the GradCam process, and the falling rate metric. Our results comprehends, first, the performance of the test phase on the clean examples. For scenario one, in X-ray images for binary classifications in the test phase, we achieved the best scores for the Inception V3. And this scenario two, we achieved the best scores for VGG 610. And the second analysis is the vulnerabilities analysis. The vulnerabilities, the first step here is the falling rate. A falling rate indicates the rate at the model is falling by adversarial examples or the perturbed images generated by the attacks. And a high falling rate represents the most harmful attack. And this graph indicates our result for the falling rate. Its epsilon or its noise level is increased and for every case, the FGSM is the lower falling rate, achieves the lower falling rate. And the deep full for every case is the harmful attacks and achieves the higher falling rate. And second scenario, we have the VGG for mood classifications in OCT images. FGSM also achieves the lower falling rate in this scenario. And in this case, for the 0.1 noise level, the deep full and the PGD are close in the falling rate. However, for every case, the deep full achieves the best scores. And the second vulnerability analysis is the GradCam analysis. And in these experiments, we random select one images, for example, one X-ray images with label pneumonia. In this label, the GradCam should pay attention in this region. When we apply the attack, the FGSM attack, the GradCam did not recognize one region to identify in our decision process. The PGD identifies a small region, different than the actual region. And the deep fools identify a wide region and confuse the model. And second scenario, we select the images, the Drusen images. The model should pay attention in this region, the grad can pay attention in this region. However, for FGCM, it's not affected by the attack. The grad can is not affected by the FGCM attack. However, when we apply the PGD and the deep fool are affected, the deep fool is split the detection in two regions, and the PGD is split the detection in two regions, and the deep fool, the detection focus outside the regions of the interest. And our conclusion, adversarial attacks could make the models misclassifications, can attack these models, and induce the misclassifications of these models. And the Gradkin heat maps can help to identify the decision process and identify these attacks, the images was attacked. And the deep fool for every case achieve the most harmful attack in these cases. As a feature work, we hope testing other attacks, for example, the one pixel attack, or water attacks, and explore their potential in real-world applications, as well propose the defensive methods. We propose attacks to create powerful defensive methods also. And the source code are available in this link, in this QR code. Thank you for your attention. Sorry.
So question is, so once the image is attacked, you will evaluate for the diagnosis or not?
Right. You mentioned the watermark attack, right? The adversarial attack is a little bit different watermark attack. In this case, we generate this noise. In our example, to see this attack, we generate a high noise to observe this attack. Usually in literature, we analyze a little bit noise, it cannot observe. Right? Watermark, sometimes we can see in imaging. It's different in this case.
As far as I understood, these attacks are maliciously, like from could this somehow happen also from like a false sensor, like there is, if I'm thinking of visual data, then maybe a crack in a lens or something? Did you analyze this?
No. Did not analyze for example, defensive mods to identify. It's all the future works we hope we analyze in this context, propose defensive methods, for example. Okay.
Actually, my question is on the following. If the model tries to explain itself, we would expect that it would actually say here there was an attack.
Right. For example, one attack of the explainability model, for example, the model was confused by attack. For example, did not identify the region. When I proposed the model and applied the grad can, any region is identified by this model. When I apply the attack, for example, the FGSM example, in here, for example, did not identify. Então, so we can conclude, for example, the image was attacked. For example, in this region. I did not was clear.
I missed exactly the explanation part, but perhaps we take it off the record also in the interest of time. Are there other questions? If not, yeah, of course, thank you very much, and I would like to thank all the speakers, all the three speakers, and thank you. Now, as you notice, we are very early. This is because we are in shorter session. All the other sessions are a little longer, so I would like to encourage you to join the other sessions for the last minutes. Keep in mind, all of them have started late, so there is some hope that we have one full paper, and then we meet again at the latest by the coffee. Thank you very much.
Good morning to everybody. Welcome. I'm Matteo Spezialetti. I will be the chair for this session. It's the first of two sessions about computer vision. And if I understood, we have 4 contributions that are all regular papers. So speakers has around 15 minutes plus 3 minutes of question time. And I think that we can start with Dr. Guerrero, that will present a multimodal image registration system for histology images. So whenever you want, you can start.
Thank you very much. Yes, I am Rodrigo Escobar Guerrero, and I will present a multimodal image registration system for histology images. First of all, what is image registration? Well, we can define it as the process of transforming into common coordinate system 2 or more images from the same scene. These images could be taken for different times, from different point of views, or from different sensors or devices. In histology, we can use it in 3 main areas. First of all, as 3D reconstruction. Here we can see an example when we have a tissue that we cut it in slices, and then we made a registration for create a 3D reconstruction or model. Also could be useful for combination of different slides with different stain methods. And finally, for the registration of different modalities, in this case I am showing you is non-linear modalities with bright field images from different microscope techniques. There are huge challenges. First of all, in digital pathology, there are large image sizes, very high resolution, normally in gigapixel resolution. So a common resolution is 100,000 pixels by 100,000 pixels, so it's very big. We have repetitive textures, non-linear elastic deformation, occlusions, missing sections, among other challenges. That's why our objective is develop a cloud-based system for multimodal histological image registration that provide user-friendly interfaces, an efficient algorithms management, and a comprehensive visualization tools. For this task, we propose an architecture with 3 main models. The first model is a project manager that allows us to create, read, update, and delete projects, and also connect with the database. The second is an algorithm manager that allows us to made association with a project and load multiple algorithms for testing for image registration for different purposes. And finally, an image visualization system where the user can interact with the images, navigate across them, and visualize the results of the registration. As I mentioned before, one of the main challenge is the very high resolution images. So in our software, we are using a pyramid organization where we have the original resolution, and then we reduce the resolution in every level of the pyramid, and also we create small sections that we call tiles. And in that sense, we can only load in memory the tiles that are being used for that point of view, and with that particular resolution. An example is in Google Maps, when we navigate across the zoom, we only load the tiles that are using for that resolution, and in that case, we don't overload the memory. We are using as backend Django 4.1, as front-end JavaScript, HTML5, CSS, and for Java responsive design, we are using Bootstrap 5.2. For the database, we are using MySQL, and for make easier deployment, we are using Docker, in particular 2 main containers, one for the database and the other for the web service. Here we can see a video of the user interface where we can see different projects. We can create a new one. All the text fields and all the inputs are validated by regular expressions. We need to load the fixed image and the moving image. We can assign to any project a number of algorithms that have been registered in the database. So we can assign only 1 or 2 or 3 or any algorithm that we want to test. And also with our software it's possible to add annotations and use the same geometric transformation that we use for the images for the annotation. Now here we can see part of the viewers that we can explore. Here are some examples. And we have 3 main selectors. One is for the images that is associated with the project, the algorithms, and the different viewers that we want to extract. In this particular case, we are using SIFT, that is very common image registration algorithm, and we can explore the feature extraction that were detected for this algorithm. And also we can explore the machine lines. I don't know with the projector if it's possible, because are very thin. We need to improve to make it more evident, these lines or matching lines. Also, we can visualize the result of the registration, that is the image that we already transformed the coordinate system. We can overlap it with the other image, that is the fixed image, in a chessboard view, and we can modify the number of the axes in the columns and in the rows to interact and visualize if the registration was correct or not. Finally, as I mentioned before, we can add annotations that it was made in for one modality, and we can use the same geometric transformation for put it in the other coordinate system. We can change the color of the annotations, and we can have as many annotations that we want. And here there are only 3, that is the crypts, the mucosa, and the background. We can show and hide the annotations. Sorry, something happened. Oh. Oh. It's not responding.
Try to stop the presentation.
Yeah. We start the program. Sorry.
Okay, well, just 1 second. Okay. Also, the video has a giga resolution.
Maybe it's possible. Yeah. Okay. Well, as you saw in the video, every project have 4 main buttons. For actions, the first button is for execute algorithms pipeline. So we can execute all the algorithms that are associated with this project. The second is for visualize the different views. And the last two is for eliminate the project or for download the results. As I mentioned before, we can add annotations. Those annotations could be made in 3 different ways. We can load images as RGB image or as a binary mask. Every channel must be a different class. In this sense, we have background, mucosa, and crypts, and we can create the RGB image. Support 8 bits or 16 bits for the annotations. But if we have more classes, we can use an NPC set files, that is file format for NumPy arrays. So we can have, using the same format for n number of classes for the annotations. And finally, we can load JSON files using the COCO format, that is a format created for Microsoft for the instance segmentation. It's very important to notice that all the annotation, even if we load as an images, we convert it for the COCO format. So we detect all the instances of that class, and we have the polygon of each of those instances. For test of software, we are using nonlinear multimodal images and bright field images with an stain method that is the golden standard, that is hematoxylin and eosin stain method. Here in the right side we can see the hematoxylin, and in the left side we can see the nonlinear multimodal image. In the nonlinear multimodal image is a label-free technique, is quite new, and we can add in every channel completely different modalities. In the red channel we have coherent anti-stroke Raman scattering. In the second channel we have second harmonic generation. And in the third channel we have 2-photon excited fluorescence microscopy. We test 2 very common algorithms for image registration, that is ORF and SIFT, in combination with some preprocessing stage, because the intensity of the images in nonlinear is completely different with the bright field images. In bright field images, the highest intensity is in the background, and in the nonlinear, the highest intensity is in the tissue. Here we can see a visual comparison with 2 examples. In the left example, we can see that the SIFT have a better image registration, and we can see in the chessboard view. Also, in the second example, is very important to notice that the resolution in the bright field image is lower. So it only corresponds of this part of the section, and when we made the registration, the coordinate system is changed and also the resolution of the image. So we can test that the registration was correct. So as conclusion, we present a multimodal histological image registration system to test different algorithms. It's a responsive web with multi-resolution pyramidal organization for very high resolution images, with multiple annotation sources, multiple algorithm testing, with multiple visualization tools, and provide a project manager. With 2 different algorithms on the registration, nonlinear multimodal and bright field images. And in our test, in this particular task, SIFT outperformed better than ORF. As a future work, when we write this paper, we have this as future work, but we already implemented the first 2 future work, that is add a plugin architecture for integrating new algorithms. So now we can add new algorithms as a plugin without modifying the code in the cloud-based system. Also, we add a batch pipeline for processing 2 folders with the same modalities, and we can use the same algorithm for the registration in all the images in the folder. In the future, we will add a support for evaluation metrics. As you notice, we don't have any metrics. We only have visual metrics, but in the future, we pretend to implement some of those metrics. And we will implement some new artificial intelligence algorithms. I only show you some of the good registration, but even with SIFT, not in all the cases it was a good registration, because there are a lot of problems when we stain with other dye. We need to wash the sample, and a lot of features were lost, so it's not an easy task. Well, finally, I would like to mention that this work was supported by the Maria Zlotowska-Curie ITN in Horizon 2020. Here is the web page for the consortium. We are 5 different projects particular, I am the last one, and this is just a part of my work. It's a consortium that have half part in Portugal and half part in Germany, and all the images that I used for non-linear multimodal images were taken for Leibniz Institute in Jena for photonics, and it was funding for the photonics research in Germany. Thank you very much, and it will be a pleasure to answer your question if you have one.
Okay, thank you for your nice presentation. Some question from the audience? Yes, please.
Sorry, maybe you mentioned that I just didn't hear it, but is this some sort of product you're commercializing, or is it available as an open source library?
Well, the consortium have the both part in a company and in the university part, and we decided we will put it in an open source. It's not yet available because we want to improve it a little bit more, but it will be open source.
And do you envision it being used for other similar use cases that aren't pathology, for instance, for psychology-based applications or something like that?
Now we are focusing on pathology images. We are using also in other modalities like fluoroscopy and for Raman throughput images. But since it's possible to use every image that is very huge, and it is possible just add the new plugin and load the algorithm for that purpose.
And congratulations.
Thank you very much.
Some other questions? Yes, please.
First of all, great presentation.
Thank you very much.
I have one question. Maybe you said it in the presentation that I missed it, but are you using any system to manage the images? So you upload an image to your platform, and how is it managed in the platform? Are you using a sort of an archive system, or it's a local file system?
Yes, no, we are not using an archive system, but the idea, as I mentioned, I am in a bigger project, so the idea is the integration with other system that is for image analysis of pathology and use the archive, but until now it's only storage as local folder, the images, and we are using...
what image formats do you support?
Well, until now it's only the support for OpenCV images, but we pretend to use other libraries that support for bio images. For example, OpenSlide is one library, or Bioformats library, that we can increase the number. And also, if we integrate it with the previous project that I mentioned before, we can use it with DICOM images. That is also nice. You're welcome.
Any other questions? Okay, so thank you for again for your presentation. And it's here Dr. Soleimani. Yes, I remember. I will introduce you. So here we have Dr. Soleimani.
Right? Sorry, I don't know. I'm not doctor yet.
Okay, I prefer to use the same title for everyone. So if you are professors, please don't blame me. Okay. And he will present a work entitled Preventing Pressure Ulcers by Image-Based Posture Detection.
Yes, posture detection. Sorry, how can I change it? Sorry.
I think that you can
just by, okay, yes. Thank you. Okay, thank you for having me. The title of our work is Preventing Pressure Ulcers by Image-Based Posture Detection. And I'm Rami Soleimani from the UCC University College Cork, and the work was supervised by Professor Derek Pesh. The problem that we addressed in this work was the pressure ulcers, also known as the pressure sores or bed sores, are a disease affecting skin and underlying tissue that mostly occur over bony parts of the body because of usually long-term pressure. It is really tricky and expensive to be treated. The objectives of our work was first to design a mechanism with low functionality, detecting the posture of the patient in the body, and the second, pinpointing the spot of the patient's body that is at risk of excessive pressure. Here is a flowchart of the work that our work is meant to be integrated. Here we have a mattress with the embedded pressures, and the result of the sensor readings will be in the image format. It will be sent to different units to produce the outputs, that these outputs can be used for the caregivers or can be used to issue comments for the actuators. We can see here the different unit segmentation, statistical analysis, and the detection part, and finding at risk points, and the monitorings. The database that we use in this study comprises of set of pressure maps obtained from 13 subjects. And for each subject, we have 17 variations of 3 main postures, supine and lateral, left and right, in the dataset. You can see here the details of the participant in terms of the age, height, and the weight. The first pre-processing part of our work was the segmentations. We used this pipeline, 2 pipelines, that the result of these 2 pipelines will be multiplied together, that it will give us the segmented enhanced image. One of the above pipeline is the binarization, and the below is the filtering, that I will explain both in the next slides. Here is binarizing pipeline. The first unit that we put in this pipeline is the equalizer to improve the contrast of the image, then Gaussian to smooth the image, and binarization that we use also method to binarize the image, and the closing morphology to remove the small noises and to fill the gaps. And here is the filtering part. We use the equalizer and the Gaussian, and you can see here one of the results of the filtering part. And in the last slide, it was the result. The image is the result of the binarization part. And here is the result of the filtering part. And the result of 2 pipelines will be multiplied together, and we will have this improved segmented body of the patients that can be used for the segmentation and pinpointing the at-risk part of the body. And the second pre-processing that we used was principal component analysis. It was our choice of dimensional reduction technique that can improve the classification part of the work. The classification, the posture the classification algorithm we used was support vector machine. Owing to the fact that we were dealing with a high-dimensional data points, support vector machine were able to find optimal boundaries between the different classes in high-dimensional feature space. And here is the flowchart of at-risk area detection and monitoring. First image will be before explaining, we divided the mattress in the cells of size of 4 by 4, and for each cells we have a sigma value and a flag associated with each cell. That the sigma value is the cumulative average of reading sensors for that cells, and the flag is the value that can be on or off, and it detects that part of the body which is in contact with that cell is at risk or not. In the pressure match will be fetched, then the segmentation, then we have a posture detection. And here we have an if statement. If the posture changes, the sigma value will be resumed to 0. If not, we will find n most stressed region that depends on the posture. It can be 26 for supine lateral and the 29 for the lateral posture. And then we map these found regions to the corresponding cell of the mattress. Then we update the sigma. Then we have another, after each period of T time, we will update the flags that I will explain the equation for updating flags in the next slide. And here is the whole loop of monitoring part. For the flag, if the previous status of the flag was 0, and here it's a term for the sigma, which is the cumulative average of the pressure reading. If it's more than a threshold, which is the empirical data, the flag will turn to on. And if the previous status of the flag was on or 1, and the pressure, the cumulative average or sigma value falls behind the P minimum, which also is another experimental data, the flag will change. For the classification part, we have these results. We evaluate the performance of the model with the different metrics for each classes and overall performance of the model with the accuracy. Here is the table for the range of PCA, principal component analysis. And as you can see, the model performs very well with this data set. And to compare our classification part of the work with other works, we used another public data set that was available, and the model generalized well with this new data set. You can see the overall accuracy was 99.2, and here is the confusion matrix for the different classes. And in these tables, we compared classification part of the works with other works, existing works. And you can see the classification part performed very well compared to other works due to good pre-processing. And here is the two examples of pinpoint at-risk parts of the body of our simulation for two different postures. And here is a snapshot of sigma and flag values for another simulation. Thank you for your attention. Thank you very much for your attention.
So, thank you for your presentation.
Thank you.
There are some questions. Any questions from the audience? Okay, I have. I'm wondering. I'm not sure if I understand everything well, but you use the data set in which there is not static images.
It's a pressure map.
Yes, but not static. There is a time component.
Yeah.
Also.
I don't get exactly.
I mean, it's the pressure maps along time.
The pressure maps with the different frequency that we can average these pressure maps for the time period, specific for just, for example, for a minute.
So you didn't use the time component?
No,
you didn't. Just static.
Just static. It was not time series.
Images.
Yeah.
Okay. Okay. Are you thinking of using some other machine learning techniques?
We used deep learning, but we came to this conclusion that the support vector machine overperformed other models, because usually these days we are overwhelmed with the deep learning, but sometimes classic machine learning will perform better in some cases. Depends on the use cases.
Okay. Yeah. Thank you. Thank you for your presentation. Yes, sure, please.
You said that you average the pressure maps over time
Yeah.
to get the images that you got analyzed. Have you considered using other kinds of ways to process the time component to learn
And maybe in the future works we will do, instead of averaging, we will have that alternative that we can use in the future works. Because it's
Is there always a time frame for averaging, the same time frame for all the instances?
The time frame was the time frames for the monitoring part, not for the classification part. For the monitoring part, it was experimental data. For example, 10 minutes. During this 10 minutes, for example, in every 20 seconds, we average the sensor readings for that cells. If it's at the risk part of the body, then we compare that with the P maximum value. I don't know if I explained exactly.
But was that duration equal for all patients?
It can be personalized. It can be personalized in the, because it's just academic or it gets commercialized, you can do more personalization for the different patients. Yeah. Thank you very much.
Yes, please.
Does it take into account the different sensitivity of the skin depending on the bones, how near the bones are to the skin? It's not a problem if there's a thick layer of fat between, but if there's only a thin layer of fat and the bone back, the white method or the pressuring method is not the most important.
Because we use the pressure sensors, we can use another modalities. I have seen in other works, but in works we use just the result of the pressure sensor readings. That we can't do that image analysis, as you said. If I got exactly what you mean.
The problem is not only the pressure support, but only the type of tissue behind the skin of the bones and skin is important for the whole process of damage.
Between the pressure, because we didn't consider that. Yeah, we didn't consider that. Maybe it's another, because we more focused on the pressure on the skin. We didn't consider the pressure between the skin and the bones. Yeah, as you said, for the different bodies, it can be different. It was just. We use average. We use average we use average. It is in details in the papers because it's just the 20 minutes. It was the long work, and it is quite detailed in the paper.
Okay, there are any other questions from the audience? Okay, so
Thank you very much. Thank you. Thank you.
And is there the third speaker? Yes. Introduce you. You are the first author?
Yeah.
Okay, so I hope to say your name correctly. Nasiri Agigi, Dr. Nasiri Agigi. Okay, so welcome. And the work is about action recognition in video recordings from gynecologic laparoscopy.
Hi everyone, my name is Sahar Nasiri Haqiqi, and I'm a PhD student and a researcher assistant on the Squash project under supervision of Professor Klaus Schaffman in Klagenfurt University of Austria. And I'm here to present our paper titled Action Recognition in Video Recordings from Gynecologic Laparoscopy. First, I'll give you a short introduction and describe our proposed model, the evaluation of result, and the conclusion. So, a laparoscopy is a kind of a surgery that allows a surgeon to access the inside of the abdomen without having to make large incisions in the skin.
It's also known as a keyhole surgery or a minimally invasive surgery. Laparoscopy can be used to help diagnose the different conditions that develop inside of the abdomen, or also used to removing the damaged tissues or removing sample tissue for further testing. And this surgery, laparoscopic surgery, has many advantages like shorter hospital stay and faster recovery time, less pain, reduced scarring, lower risk of infection, better visualization, and so on. Laparoscopy, in laparoscopy, large incisions can be avoided because the surgeon use some instruments called laparoscope. Laparoscope is a small tube that has a light source and a camera which relays images of the inside of the abdomen to the television monitor. And these images on the monitor are used as the eye of the surgeon, and the surgeons can control and supervise the actions that performed with the instruments. And also they record the whole operation for different purposes, like teaching operation techniques to young surgeons, post-operative explanation to patients or discuss with other colleagues, preparing follow-up surgery, evidence in the case of lawsuits, and the most important one, surgical quality assessment. In surgical quality, the most important purpose of recording these videos is the usage for post-operative analysis in the course of surgical quality assessment. There are two methods for this purpose. The first one is OSATs. That, as you can see here, there are different tasks that they score them, and they can measure the surgeon's skill level. And the second method is called GERT, which is more specific, and it defines 4 different errors. It's too much force, too little force, wrong orientation, and inadequate visualization. Someone should watch the whole video. It's like 2 or 3 hours, and fill this form and say these errors happened, when happened, and describe it. These 2 methods are really significantly improve the quality of the surgery, but it's really time-consuming and error-prone. And here you can see some errors in these videos. The first one is cutting, that it's too much force, and as you can see, it's cut the vein. Sorry about that. It's a little. And the second one is on grasping detection, but the error is too little force, and as you can see, it cannot grab the tissue or the organ. And the second one is abdominal access, and again, it's too much force and also inadequate visualization, that the instrument is going to the organ. Yeah. So these are the errors that happen in laparoscopy surgeries. The main aim of this research is to learn and classify a specific type of technical errors in this surgery, and to distinguish between a correct and incorrect moves or actions in surgical events. But in this stage of our study, the aim is that to learn and classify different types of actions in laparoscopic videos. So our proposed model is to recognize different actions in these videos. This is our framework. The first part is the training part that includes the data sets, data augmentation, and frame sampling, and our CNN-RNN model. I should mention that it's a multiple binary classification, which we recognized 6 different actions. Our target action are abdominal access, grasping anatomy, knot pushing, needle pulling, needle pushing, and suction. So I explain each part in detail. The first one is the data sets. We have the whole video. It's like 20 minutes or even more, maybe 40 or 50 minutes. And I explain it for the first action, the abdominal axis. In the whole video, we extract just the abdominal axis part and put it in one category, and the rest of the video, it includes different actions, and sometimes it's not any actions, it's just without any instruments, and put them as the rest category. Here, all the video clips are about 2 or 3 seconds, but the problem is that it's very imbalanced, these data sets. So to address this problem, we apply different data augmentation techniques like gamma contrast, Gaussian blur, brightness, saturation, and horizontal flip. Now that our data sets are balanced, so it's time to for frame sampling. Each video clip is 2 or 3 seconds and with 25 frames per second, so it includes 50 or 75 frames that we sampled just 20 frames of each videos, and these sequence of frames are fed into our CNN-RNN model. This is our model. It includes the CNN part. We use the CNN part as a backbone to extract different features, and we use different networks like VGG16, ResNet50, EfficientNet, and DenseNet. All these networks are pre-trained on ImageNet, and the output of this CNN part is our feature maps. These feature maps are fed into the recurrent neural network, and the recurrent neural network is for temporal information, and also we also use the different recurrent network like LSTM, GRU, BiLSTM, and BiGRU. It's just for compare their performance. After the network, I used a dropout layer and for regularization, and to dense layer, and then softmax. So now our model is trained with our data sets, and now it's time to test the model. For testing the model, I explain it here in detail. Now we have the whole video again, without any annotation. We split it into just 3-second video clips and predict each of these 3-second video clips as an abdominal axis or rest, like this. Predict all the 3-second video, and it's like predict the whole video. This process is just for abdominal axis versus rest. Now we repeated this process, the whole process, for other actions, and grasping anatomy, knot pushing, needle pushing, and suction. And at the end, we labeled them as, for example, grasping anatomy or rest. Now it's time to evaluate our model. And for evaluation, we use the accuracy, precision, recall, and F1 score, which are the most important metrics in classification problems. Here, this table is the accuracy. It shows that the different CNNs, the combination of different CNNs with RNNs. And for example, in the first one, the VGG16 combined with LSTM, GRU, BiLSTM, and BiGRU, and these are the accuracy for different actions. And the first one, fully connected, is just the CNN. It's without any RNNs, and as you know, that CNN don't consider the temporal information. It's just frames, so it's like a frame classification, and you can see that the accuracy is much lower than when we combine the CNN and RNNs. And here, the combination of ResNet50 with the RNNs has the best results. And for example, in grasping anatomy, we achieved the accuracy of 93.45%. And you can see that, for example, for the action needle pushing, needle pulling, the accuracy is a little bit lower, and it's because these two actions, and also not pushing, these three actions are very similar to each other, and it's really hard to recognize them. And because of that, the accuracy is a little bit low. But on average, the combination of ResNet 50 and BioLSTM has the best result of 86.78%. And here, the F1 score, you can see the F1 score, recall and precision. And yeah, again, it's just for ResNet 50 with other RNNs. And yeah, you can see the average that BioLSTM is the best one. And here again, you can see some example of that, these are surgical videos that our proposed model recognized. The first column is the ground truth is abdominal access. The green border means that the system recognized it correctly, but the red border is that it recognized it wrong. The first one is abdominal access and recognized as abdominal access. This one is abdominal access but recognized as rest, and maybe it's because you can see that it's like inadequate visualization. The instrument is not completely on the scene. The second one is grasping anatomy, which is correct, and this one is grasping anatomy but recognize it as rest, not pushing, and yeah, it's recognized it as rest. Needle pulling, which recognizes it correctly, and this one is needle pulling, needle pushing, and yeah, it's needle pushing. And you can see that these two are even not pushing, they are very similar to each other. It's just the needle that pull and push, and it's really hard to recognize. And the last one is suction, and yeah, it's suction but recognized as rest. Now the conclusion. Our main contribution are providing a comprehensive comparison of various neural network architectures like static CNNs and end-to-end CNN RNNs, and proposing a CNN RNN architecture for recognizing different actions with promising accuracy. And also our work are focused on the full video based. It's not just frame. It's we consider the full video based. And last but not least, we generated these data sets and publicly releasing this data set with customized annotations. Thank you so much for your attention.
So thank you. Are there any questions, please?
Yes, what's the number of videos for each type of action that you are trying to see the number?
Yeah, for the number of video clips for the training set, it's just after the data augmentation, it's like 200 video clips for each class. And for test, it's like 40 or 50 video clips.
I don't understand if I learn hybrids or pedestrian crossings and other things, you know that from Google. India is a company labeling millions of pedestrian crossings, millions of hybrids to teach such a network. I cannot understand how this will work with only a few hundred or...
Yeah, I know. So this, the data sets is very important, and we kind of lack of data sets. So we have to train the model with just like 200 video clips for each class. But we are working to generate more data sets. We collected our data sets on the Medical University of Vienna. And yeah, we are trying to provide more data sets for that, for our future works.
Any other questions, please?
In terms of accuracy, you were mentioning some techniques to measure
Have
Have you ever considered using some of their measures, some of their measurements, what they are used to?
we use their annotation for the, calculating the accuracy. It's the annotation that's, it's with the videos. I'm not sure that I understand your question, but the accuracy is that, for example, when it's 93% accuracy, it means that in the whole test set, it's 93% of the videos it's correctly recognized, and this is the accuracy. It's the total number of correct videos that predict correctly over the whole data sets, the whole videos in the test set.
Over all the videos that
Over the
polling, for instance?
over the whole video clips on the test set.
Okay, I understand.
Mm-hmm.
Thank you.
Yeah.
Yes, please.
I may have a question that is sort of two in one. How do you intend, you said you were going to, as a future, you will explore using whole video clips. How do you intend to do that? And maybe there is some question maybe on your answer.
Yes, we consider the whole video and just split it into 3-second videos without any overlap, just 3-second video clips.
Not about what you did in your future work, in your conclusions, you said that in the future you want to explore using whole video segments. And I see that the network you developed for the analysis of frame, analyze each frame independently. So my second question was if you considered stacking the set of frames that you sampled from the video, for instance, instead of just directly analyzing each frame separately.
In this work we use the whole video. It's not just for our future work. In this work we consider the whole video, and
Not my question, but you do not process the network you develop does not process video content. You mentioned that it just processes each frame of the video.
No, we didn't consider the frames. We considered the videos.
Okay, maybe I read it.
Yeah, sorry, I didn't understand correctly your questions.
Any other? Please.
Did you do any cross-validation? As the same thing is related and use small. So besides testing data, did you use any kind of cross-validation to show the generalization of the results over the whole data?
The cross-validation?
I think it's intended to split your data set in several cross-fold. And each time you train by, for example, in one out.
Yeah, I understand. No, we didn't do that. No.
I have one other question. What is the decision threshold value to get a positive result?
Sorry, I didn't
What
hear.
is the probabilistic decision threshold value to get a positive outcome in your case? Is it more than 0.5 or do you use any distinct?
No, the threshold was 0.5. Yeah.
Actually, I have a. Are there any questions from the audience? Actually, I have also one. Is there a specific reason, or I don't know, to define a set of binary classifiers instead of a multi-class approach? Because, for example, in this case, you are facing a problem of unbalanced data set because you are using one class against all the others. What about using
Multiple
directly 6 classes?
We did that. First we used the multiple classification, but in this case when we use multiple binary classification we have better accuracy. We can recognize actions with high accuracy, and it's the reason that we use binary classification for that.
Okay. Okay. Thank you for your
Thank you.
Thank you. So, Dr. Sampaio.
Dr.
Okay, I did everything wrong. Sorry, but she will present an AI-powered image acquisition and characterization of dressing.
I think we need to change something.
Patient-centered wound management.
Hello, my name is Ana Filipa Sampaio, and I'm here to present my work entitled AI-powered image acquisition and characterization of dressings for patient-centered wound management, on representation of my colleagues, namely Pedro, which was the main author of the paper. This work was developed in the scope of the Clinical Wound Support Project, whose main goal is to develop a mobile application to support wound monitoring by nurses in care homes and other healthcare facilities. And wants to facilitate and streamline the different processes that are associated with proper wound management, monitorization, and documentation. So it was developed in the context of chronic wounds. Chronic wounds are wounds that do not undergo at a very timely and normal healing process. They are very hard to heal and currently have a very high prevalence worldwide, which, associated with its high impact in the patient's life quality and in the healthcare institutions, makes them a very relevant problem with considerable costs associated. For a proper evolution, the wounds should be closely monitored and documented by experienced professionals, and for a proper treatment, the management of the wound dressing, I mean, everyone knows what a wound dressing is, the coverage that you put on it, that aims to protect the wound and prevent further contaminations, is essential. And this is usually performed by trained nurses by inspecting its outside and the presence of a substance called exudate, which is a substance formed during the inflammatory processes of the wound healing, and that is absorbed by the dressing and sometimes visible on its surface. However, even though this correct assessment of the dressings and of when they need to be changed is essential for a proper evolution of the wound over time, in many cases the patients are not at clinical facilities and do not have access to clinical staff monitoring them on a daily basis. And that responsibility is the responsibility of informal caregivers that lack the specialized knowledge to do this assessment properly. And for this reason, there is a current need for research in a more patient-centered wound care and treatment solutions that in the past few years is still lacking in the research area. And for this reason, in the Clinical Wound Support Project, we decided to include a module targeted for informal caregivers that supports the assessment and monitorization of the dressing state. This dressing analysis pipeline that we're proposing encompasses two main modules, or sub-modules, if you may see, namely an automated image acquisition methodology that facilitates the acquisition of standardized images of the dressings of the patients, and a second module for the analysis of the dressing images captured by the acquisition module that characterizes its state, either if it needs to be changed or not. The image acquisition module is based on deep learning models that are responsible for localizing the dressing and an adhesive reference marker that will be used as a metric reference, as I will further explain. And then these regions are then processed by an adequacy validation module that checks if the image complies with the clinical adequacy requirements that were identified by clinical staff, namely the presence of these two structures, along with the presence of a sufficient peri-wound or peri-dressing, in this case, radius of at least 2 centimeters. And that's why we need a reference metric used as that adhesive marker that you will see in some images in a while. Then we have the dressing characterization module that evaluates the state of the dressing, indicating if it needs to be replaced or not. These two modules were integrated in a mobile application in order to provide a tool that facilitates the communication between informal caregivers so that they can more easily see if the dressing needs to be changed, and if so, contact an experienced professional to do so. Moving on to the development activities. Since since there was no actual data set with easily usable metric reference markers available and dressing images, we constructed a novel dataset comprising images of wound dressings and reference markers that were acquired by clinical professionals, namely experienced nurses, from 9 Portuguese healthcare institutions. And these images included dressings from different types of patients, from different types of wounds, from pressure ulcers, as my colleague mentioned before, to diabetic foot ulcers, to leg ulcers, all kinds of ulcers, and these images were stratified in 3 types of dressing status. Either saturated, meaning that the dressing has an amount of exudate above its absorption capacity, usually set at 75%, with exudate leakage, meaning that regardless of its saturation state, there is exudate in the border of the dressing, so it needs to be changed, even if it is not above the 75% of absorption capacity, and either clean dressings that can be completely clean or with just a small amount of exudate that doesn't require changing. This resulted in a total of 193 images, from which we had 6 just saturated, 33 with exudate leakage, 16 with both conditions, and 138 clean dressings, which is highly unbalanced, as you may see. All these images were annotated in terms of labels and in terms of the saturation stages by 5 different specialists in wound and dressing care, and the dressing and marker boundaries that you can see here in the examples were annotated by us, the researchers. Regarding the development of the detection module, we used an object detection model, namely a RetinaNet architecture with a MobileNet V2 backbone, which was selected taking into account the need for deployment in a mobile environment, since it has a good trade-off between a fair detection performance and a reasonable computational complexity. And due to lack of time, we subjected it to a random search hyperparameter tuning, in which we only optimized the batch sizes and learning rates. And these 2 hyperparameters were randomly sampled from adequate ranges, resulting in the 3 main experiments that you can find in this table. For the training, we used the outcome optimizer and the Uber regression and the focal cross-entropy losses for the localization and classification tasks, respectively, as well as the weights from the common objects in context detection dataset to initialize the network. Regarding the data, we divided the whole data, from the whole data set, we used 75% for the development of the model and subdivided this 75% in 3 cross-validation folds and kept the remaining 25% separate for an independent test analysis in the end. The stratification or the division in the different subsets, both at the train test level and at the cross-validation level, was performed in a stratified manner in order to ensure that images from dressings of the same wound were always kept in the same subset and not in different subsets to avoid biases in the evaluation process. Apart from this, all the images were resized to 320 by 320 pixels for standardization purposes, and they underwent dynamic augmentation during the training process. The hyperparameter tuning experiments were evaluated considering common object detection metrics that you can see here, namely the mean average precision and the average recall, and we considered the average cross-validation values to perform that evaluation. After applying the detection model, the outputs of that model were used by the adequacy validation model to verify if both the structures were present, and then consider the size of the marker's bounding box, which has a fixed size of 2 by 2 centimeters, to check if we had a sufficient peri dressing, in this case margin, all around the dressing image. Although, since the dimensions of the marker are 2 by 2 centimeters, we tested empirically with clinicals and with real dressings and found that the optimal multiplier factor of the side of the marker was 1.5 instead of just 1, so this was the one used and finally deployed in a mobile application that was then assessed and tested with clinicians, as you may see. Moving on to the detection results. We can see here, maybe it's not so clear, but you have the performances per class. You can see that the marker, the ones in the middle, has a slightly higher performance than for the dressing, but that's probably due to its very simpler shape and colors. But regardless of that, both of them exhibited similar performances and fair performances. And if we compare the three experiments represented by the different colors, we can see that experiment 3 yielded the highest cross-validation metrics. So these were the parameters selected as the final ones and used to retrain the model on the whole training set. And then this retrained model was used to obtain the test set results that, when compared with the cross-validation results, are slightly below, but still in the same order of magnitude, which attests that despite this slight decrease, the model kept being robust and sort of reliable, so it was a good indicator. Sorry. If we analyze in more detail the examples of predictions, as you can see here in these examples, we can understand a bit this decrease in performance, which has to do with the instances and the images present in the test set. For instance, if you look at images A and B, you can see images of specific types of dressings that usually are not addressed by are not so common and weren't so common in the training set, and that's why it failed. And despite that, we can see that the model has a fair detection robustness for myriad detection conditions, even with more skewed images and different types of wounds, which attested its robustness. And apart from that, we also, as I mentioned, included this model and the adequacy validation module in a mobile application and tested it in a mobile environment in 2 different smartphones, a mid-range smartphone and a high-range smartphone, and accounted the time for each processing step, and we found that the detection model was the most time-consuming step. But regardless of that, we still had a very responsive application, which I should be playing the video right now. Sorry, I got carried away. Here you can see the acquisition application working. So in this framework, the user points and tries to center the dressing in the image. The modules are running frame by frame while the feed is running, and then as soon as the detection model detects both structures and the adequacy validation ensures that both of them are present and that the peri-wound radius is present as well, an image is acquired with success. Moving on to the dressing classification module. From this dataset distribution, we can see that we had, and from what I already mentioned, we can see that we had a very imbalanced dataset with a clear dominance of clean dressings and an underrepresentation of dressings with exudate and with leakage. So we decided to merge these 2 classes, since what the main output that we were interested in was finding out if the dressing needed to be changed or not. So we turned this into a classification problem and merged all the instances from these 2 classes. But despite that, we still had a very imbalanced dataset, so in our experiments we applied some strategies to try to compensate for that. Namely, comparing using the dataset as it was with a slightly downsampled dataset, in which we selected a few instances, I think it was about 30 or something, I'm not sure, from clean dressings that were easy to classify and remove them from the training dataset, and as well as applying different types of transformations, namely geometric image transformations and intensity-based image transformations, always validating the output, in different proportions to get different distributions of data. So we tried in 2 ways. In the one experience, we will see that of the first symbol, we perfectly balanced the 2 classes, the clean dressings and the change dressing and the no change dressing. And in the second case, we just doubled the underrepresented class, which in the end was still a bit unbalanced. Apart from that, all images were preprocessed according to and cropped according to the detected the regions, the dressing regions detected by the detection model, and where a small padding was added to ensure that we got a square region to standardize the input for the networks, which was then resized to 224 by 224 pixels. Besides this, we also conducted some additional experiments to add a small margin around the borders of the region of interest, because we noticed that although for training we used the ground truth annotations that were annotated directly in the images, when we ran the detection model, it had a tendency to crop a bit the regions and to encompass too much of a very narrow region of the dressing. So we tried to test if using an additional margin defined according to a percentage of the marker size was also beneficial, and you'll see those results afterwards. And apart from that, we tested 3 different models, 2 convolutional neural networks with different complexities, namely the mobile net v3, a small version, and an efficient net v4. And these 2 networks were tuned in terms of batch size and learning rate under a grid search process, and optimized with the Adam optimizer and the binary focal cross entropy loss, also to address the imbalance issue. Apart from that, just to establish a baseline, we investigated also using a support vector machine with a linear kernel and using the histogram of oriented gradient features. In addition, we also experimented with 2 different color spaces, but just a very brief experiment comparing the usage of RGB images and grayscale images. From these results, in here you can see the results of the 3 models, the mobile net, the efficient net, and the SVM, with the color space that yielded the best performance for each of them, and with a different datasets. So the O is the one without any processing, without downsample. The D is the one that has downsampling. The underscore A is the one that has a perfect application of augmentations in a perfect way, and the A2 is the doubled underrepresented class. From this, we could see that the most promising model was the mobile net v3, although the efficient net provided some equivalent results, but it showed very higher standard deviation, so we opted to go with the mobile net. And despite that, the results for binary classification are not optimal. They could be much better, and this probably has to do with the low quantity of images, the still persistence, high dataset imbalance, and also with a lack of coherence in some annotations and in the difficulty of the tasks, which you will see in some of the cases I will show in the end. Apart from that, as I mentioned, we did that experiment with adding the padding. This was the padding added to the ground truth bounding boxes, and when added to the ground truth bounding boxes and trained with those, the padding, the extra padding around the region of interest did not exhibit any improvement in the classification of the dressings, but then we retrained the whole mobile net with the ground truth annotations without any padding and tried to assess the test performance without padding using the regions of interest annotated by the ground truth and using the regions of interest detected by the model. And when using the bounding boxes detected by the model, the padding actually improved the results. So when using with the model, we found out that a padding of 0.5, the marker size, was optimal. And here you can find, maybe I shouldn't look backwards, sorry. Here you can find some examples of the test sets that exhibit why it's hard to classify and why this is a very hard task. For instance, in here you can see a clean dressing that has a lot of shadows that should be, that can be confused with exudate or with some dirtiness in some cases. Here you have a still usable, I don't know if you can, but yeah, you can see. A still usable dress. Here you have one with leakage that isn't really visible. And here you have a saturated, in the last one, you have a saturated dressing with leakage that it's not, at least for me, it's not visible, even in the computer. I know that the intensity here is a bit distorted, but it's not visible that you need to trench this dress. It completely seems like a clean dressing. So this is, although the results were not optimal, this is a hard task, and this was a good first step. Just to recap a bit what you just saw, we could actually implement with success the acquisition module, and this is of utmost importance, especially for scenarios as we can, as I described in the case of informal caregivers that are not trained and would have a lot of difficulty in acquiring proper images. So this helps a lot. And apart from that, although the dressing classification module still has results that should be improved before a clinical deployment, it was a very good first step and the first approach, to the best of our knowledge, to address this vision, this as a vision task. So it provides a baseline and for further work that should be improved through the improvement of the data set, and maybe even through a more detailed exploration of machine learning methodologies with more targeted features that, in the case of such a small data set, may be profitable. Apart from that, as I mentioned, this was a very good first step and a first step for the advancement of a more patient-centered wound care that facilitates the lives of informal caregivers without focusing only on the clinical facilities, and addresses the reality of many people. So thank you. Sorry for speaking too much. I think I extended it. I get carried away.
Thank you for your presentation. Please.
Thank you very much for your presentation. First of all, did you mention for reduce the imbalance, did you only use the downsampling? Did you try to use with an on-sampling or use a hybrid method where you use a different loss function that is focused in imbalance deficits?
Precisely. I think I mentioned it, but maybe not enough in the middle of so many information. We actually used not upsampling, because something that we found out, as you, maybe I can show the results of that augmentation. We found out that only doubling the underrepresented images, not through upsampling, but through augmentations, was superior to perfectly balancing the dataset. So doubling the instances while keeping it slightly imbalanced was superior to doubling them, probably because when we completely balanced the dataset and the two classes, we were repeating too much information. So by creating new instances of even if they're transformed, of the underrepresented class, it wasn't adding any information that was helping the network learn. So upsampling wouldn't work as well. We didn't try it, we tried it just with augmentations, but since we had this variability issue with just augmentations, I think upsampling wouldn't work as well. I don't know if I answered your question, but you did another one. But we also used a focal cross-entropy loss. It's not in the slides, but we used for the classification of focal cross-entropy loss that was supposed to address specifically that problem.
My second question is regarding for the method that you use, that is an average precision with an intersection convergence of 0.75.
Exactly.
Probably when this mean error precision is a step for the average precision, because you have the mean between 0.5 to 0.9 with steps of 0.5. Normally when you use mean error precision is the mean of those thresholds. Why did you put mean error precision instead of average precision of 0.75?
I don't know if I completely understood your question. Are you asking me why didn't I compute the mean average precision overall, the one that is obtained by integrating the results over different thresholds, it's the area of the curve of the mean average precision, or if...
There is a confusion, even in the literature, when you use mean average precision, there are some authors that they only use one threshold, as you, 0.75. But normally, mean average precision is the mean of many different thresholds, starting from 0.5 to 0.95 with some steps. So you measure all these steps, and then you meet the mean of those.
Okay, I see what you're saying. I'm not sure if it's that way. I think they call it the mean average precision because they average it over the different classes.
Okay.
And that, but when you do, I'm not sure, I may be incorrect here, but when you present just the mean average precision, usually they use it, as you said, they integrate it over a range of thresholds. We selected a threshold of 75% of the intersection over union because we needed a high threshold that had a good performance and a good overlap with the ground truth, but in some cases the ground truth annotations weren't perfect as well. And in some cases it was a lot hard because we only segmented the absorption area of the dressing, but there are some dressing materials in which you can't really pick it up and there's a high variability, so we also wanted to be a bit flexible in the threshold so that we would accommodate that variability and that uncertainty that we had in the annotations.
Please. Why don't you use multicolored references? There are only different colors, but single color references. If you have multi-color references, you can better calibrate your color space, so you get the true colors.
You're talking about the reference marker, right? We assessed that, but we wanted something that was easy to deploy and to use in a practical scenario. We couldn't find, there are some that have not necessarily QR codes, but have more different structures. But these were the ones that we found along with the clinical partners, because this project was developed along with a more technical partner that is developing the app and the clinical partners that are in the institutions and want to actually deploy the product and use it. These were the ones that we found that were more readily accessible, commercially available, and we tried to use different colors so that we would investigate color correction in the future, but we haven't had the chance to address that.
And as a second point, I know that there are also markers that change the color and humidity, so if you attach such a marker on your clothing, you get a
different color
indicator for the saturation than just on the color, which depends on illumination and everything else.
Can you repeat, please? Because I think I'm interested in...
I know that there are color indicators that change their color depending on the humidity of the medium level. And why not attaching such a color indicator on the dressing so you have a reference color you look for and you know the saturation. It's more simple than to look for the maybe material dependent change of color according to the saturation.
Okay, I see what you're saying, and that would be actually a very interesting idea, but I don't think that the clinical staff would be very interested in sticking something directly in the dressing because of the, how do you say I'm missing the word, the cleanliness conditions. We can only stick something not directly near the wound. We only can put it on healthy skin, and if we were to put it directly in the dressing, we would be compromising the dressing itself because we would have to ensure that it was completely sterile. That's the word I was finding out. I was looking for. Sorry, I don't know if I was. It would be interesting though, but we would have additional concerns, especially with the certification of the product as a whole, when interacting and putting something directly in the dressing, because the clinicians actually to use the app have to use gloves, and we were working with them so that we could standardize the process to make them discard gloves as much as we could do, because to use the phone they have to take a glove off, use the phone while keeping the other hand sterile and while they're treating the wound or the dressing, and then this in a clinical setting, and to use the whole app, not just the dressings module. The dressings module works without any direct interference. But we have that preoccupation and that concern that in keeping the whole region around the wound and the dressing sterile to prevent further infections. And if you were to stick something directly in the dressing, you would be compromising it.
Nurses and caregivers are so badly educated that they can't do it without computer science.
There are a lot of ways to getting there. There are also dressing materials. The current state of the art regarding dressings, we couldn't find anything concerning computer vision, but there are a lot of dressing materials that have been developed with sensors inside, as you said, that mimic colors or prevent some kind of or provide some kind of information. But usually that kind of approaches is more expensive, and most care facilities and most people that are at home wouldn't be able to afford it. I know, sorry, but it's an interesting research path as well. As a biomedical engineer, I really like to know about it.
So, are there any other questions? We have one.
Yes.
Okay. No, I mean, I'm wondering how much the detection part and the cropping of the patch, the dressing area, dressing. Sorry.
Yeah, but we confuse use that.
Sorry, no, dressing is
No, it's dressing. The patch is, I think it's when you have the ones more.
Okay. How much it impacts and affects the final outcome? I mean, did you perform a sort of ablation study in which you directly try to classify without reshaping, without cropping, in a sort of end-to-end approach?
We do not have those results here in the presentation, but we started by doing that, and it had a lot of contextual information that provided much slower metrics.
I suppose that you use this approach because the other one doesn't work. Okay, perfect.
But the model runs also with those because it uses a padding when it isn't able to detect something, it's still able to run through images without any problem.
Okay, thank you again for your presentation. And we are at the end, a little bit late.
I apologize for that.
No, don't worry. So have a nice lunch. Okay. Thank you. Thank you, everyone.
Hello, everyone. We'll start our session about network and telemedicine systems. I am not Alejandro. I am Alejandro too. I'm kidding. I am João Almeida. And yesterday I negotiated with them to be sharing the session, so we won. And we have here to present telementoring using augmented reality, a feasibility study to assess teaching of laparoscopic stuttering skills that will be presented by
Shyam Balakrishnan.
And you have 18 minutes, 50 minutes, sorry, plus 3 minutes of questions.
Okay.
Please try to keep the 15.
Try. Okay, can I start?
Yes.
Okay. Good afternoon, everyone. My name is Shyam Balakrishnan, and I'll be presenting this research findings on behalf of our group titled Telementoring Using Augmented Reality, a Feasibility Study to Assess Teaching of Laparoscopic Suturing Skills. This was a collaborative project between 4 institutions, Hamad Medical Corporation and Qatar University from Qatar, and the University of Houston in the USA, and Politecnico Milano in Italy. I'm a medical doctor by training, but our team was multidisciplinary, so we have a team of computer scientists, engineers, and surgeons in the team. I want to draw your attention to this first slide, which I'm not sure if it is clear. So this is the traditional setup of a laparoscopic minimally invasive surgery. You can see the surgeon and the assistant surgeon looking at the screen, and what they see is the feed from the endoscopic camera, which shows the surgical site. And based on what they see, they manipulate the surgical instrument using their hands, so there is an element of hand-eye coordination and visual tactility involved. So for a surgeon to reach such a stage of expertise, he needs to undergo years of training and education. So traditionally, this surgical training was done by the C1, do one, teach one paradigm. So if there was a junior surgeon, he would observe his experienced mentor, and when he became confident enough, he would do some of these procedures under their guidance, and once he became competent enough, he would do it independently and then teach the next generation of junior surgeons. So this approach is, there are some challenges to this approach. It is time bound, so the surgeon only has about 5 to 6 years to complete his surgical residency. And the amount of progress they make also depends on their personal attributes. So it could be competitiveness, diligence, accountability, endurance, etc. When you factor in minimally invasive surgery, there are additional challenges that they have to master, which have nothing to do with surgical competencies. These are psychomotor and cognitive functions, such as hand-eye coordination that I mentioned before, economy of movement, tissue handling, dexterity, etc. Over the past couple of years, when COVID hit, there was an additional challenge that we faced. The surgeons who were experts were redeployed to other regions which needed medical personnel on the front lines. So the volume of surgical expertise and training for the residents was reduced. And there was also exposure minimizing protocol. So you couldn't have too many people inside the operating room doing a surgery. So from all of these, we found that remote telementoring could be a viable alternative to in-person teaching. This would be advantageous in resource-deficient areas. It would provide an ideal learning environment without the constraint of person being available in the form of an expert or time constraints. It would address the shortage of experts and promote health equity. So by that, what I mean is everybody would have access to expert surgical training, irrespective of the hospital or the institution that they are in. This is just a pictorial depiction of our setup. We were set up in Qatar, which is in the Middle East, and the remote mentor was located in Houston. We were geographically separated. I apologize for the blurry images in advance, but this is needed to show that currently in telementoring there do exist some AR-based visual cues, such as screen annotations and overlaid hand gestures of the mentor, which could be used to set up the telementoring workflow. And also the AR tool motion has been shown for laparoscopic as well as robotic tool guidance. Okay, I'll continue. So these studies, there were some limitations. So existing telementoring platforms, they necessitate that the same laparoscopic setup be present for both the mentor and the mentee, and these systems are generally bulky and expensive to procure. And these studies also, which were published, they also had the mentor and the mentee in the same room. So this was not a usable scenario for us to facilitate remote telementoring. So our work aims to build on these existing efforts and investigate the efficacy of a synchronous remote telementoring prototype. In our study, the mentor uses a remote workstation, and he's able to connect to the training site and provide visual and verbal guidance in the form of augmented tool motions onto the screen. And on the other end, the mentee is able to follow the mentor's instructions and learn intrinsic details which are very specific to the procedure or the skill that we have chosen. So this is the methodology of our study. We chose a laparoscopic intracorporeal suturing task. This task was chosen because it was simple enough that the mentees could understand what was required of them, yet it was complicated enough that certain hand-eye coordination and surgical skills were required, and it is a common feature of almost all laparoscopic surgical scenarios. This task was further divided into 10 steps, and for each step, predefined errors were assigned, and so there was a limited number of errors that were possible for each of these steps. And we divided the participant group. The participant group consisted of 18 mentees, and we divided them into 6 per mode, and there was one mentor for each of them. The user study had 3 modes, like I mentioned. Mode 1 was where the mentee learned from watching a video pre-recorded before the task. Mode 2 was when the mentee learned from the mentor. He was in the same room, so he was physically present without any geographical separation. And this allowed him to do an instrument takeover when he wanted to teach the mentee, and it also allowed him to use his own hand as gestures to give guidance. And mode 3 was our prototype, when the mentee learned from a remote mentor. There was no instrument takeover or hand gestures, and virtual tools augmented onto the mentee's screen was used to give guidance to the mentee. I want to show you a brief 1-minute clip of the pre-recorded video that was shown as an example.
Hold the soft tissue suture pad using the non-dominant hand and place the needle through the cavity using the dominant hand. Once the needle is placed through the cavity, use the non-dominant hand to protect the soft tissue while pulling the suture thread using the dominant hand. Orient the needle in a crescent shape such that the suture thread and the non-dominant tool are parallel. Use the needle to wrap twice around the non-dominant hand. Grab the free end of the suture thread using the non-dominant hand and pull the hands opposite to each other to put the first row of the square knot on the soft tissue suture pad. Switch the needle from the dominant to the non-dominant hand such that the suture thread and dominant hand tool are parallel. Use the needle to wrap once around the dominant hand. Grab the free end of the suture thread and pull both the hands opposite to each other to put the second throw of the square knot.
As you can see, for each step there was a brief description, and also the errors associated with each step were shown to the participants, and this was used in mode 1. This is a video of mode 3 where the telementoring prototype is being used.
We'll now start the movement of the two. Suture pad using we'll bring the left tool and hold it from the tip. The cavity using the dominant hand.
Sorry, there's a double video.
Yeah. Once now bring this place through the cavity, use the non-dominant hand. Hold the soft tissue suture pad using the non. We'll now start the movement of the tool. We'll bring the left tool, suture pad using the hold it from the tip, and place the needle through the cavity using the dominant hand. Now bring the tissue to this side.
I apologize for that.
And then use the non-dominant hand to protect the soft tissue while pulling the suture thread. We'll now start the movement of the tool. Orient the needle with crescent.
Because we have some time to.
I will just reduce the volume of this one. Hopefully this should work.
We'll now start the movement of the tool. We'll bring the left tool, hold it from the tip. Yeah. Now bring the tissue to this side. And then you can see this hole, so you can put the tool inside. Yeah. If you want, you can put it more down. And then if you now will try to see this tissue over here. Now grab the tip of the tissue from this side. Yeah, and now bring the tool tissue to this. And now release the left hand. Bring the tool over here to see what's inside.
Thank you for bearing with me. So that was mode 3 in action. So this is a depiction of our telementoring setup with the mentee on the left and the mentor on the right. The mode was composed of 2 stages, and each of the modes were composed of 2 stages. Stage 1 was was the learning stage where the mentee got guidance. Okay. Stage 1 was the learning stage when mentee got guidance from the pre-recorded video, which was mode 1, or from mode 2 and 3 where the mentor was present either physically or remotely. Stage 2 was the testing stage where the mentee was asked to repeat the task without any without any inference from the guidance from the mentor or from the video. And for each of these modes, we recorded the errors per step and the cumulative errors, as well as the duration per step and the cumulative duration. So this is the results of the cumulative errors on the left and the durations on the right. So as you can see, the ANOVA we did an ANOVA analysis, and it indicated that the mode for the errors was statistically significant. The error count under the mode 1 was higher as compared to mode 2 and 3 for stage 1, and this is also reflected in stage 2. So basically this shows that in the presence of assistance from a mentor, which is mode 2 and 3, the mentees were able to learn and perform the task better than compared to simply learning from a pre-recorded video. We did not find any statistically significant difference between the error counts under mode 2 and 3. So mode 2 and 3 were equivalent in terms of the errors for teaching the technique to the mentees. On the right side, you can see the total duration of the mentoring session, and ANOVA analysis showed that the stage was significant in calculating the duration. In stage 2, the mentees applied the learnings from stage 1, and so the mentor's involvement or the need to rewatch the videos or involve the mentor for further guidance was reduced, and so you can see a reduction in stage 2 as compared to stage 1. There was no statistically significant difference observed for the modes for the duration between either stage 1 or stage 2. So basically what that means is that it took an equal amount of time for all the modes to be taught in stage 1 in comparison to the learnings in stage 2. This graph shows the time taken for the exchange of information between the mentor and the mentee pair for each step which was analyzed, and mode 1 was excluded because there was no mentor present. They were just using videos in mode 1. And you can see that some of the steps had an equally higher duration irrespective of the mode. On average, the information transfer between the both modes of training took an equivalent amount of time. However, some steps were preferred in mode 2 over mode 3 and vice versa. And this we discovered later was based on the ease of communication and the duration between the mentor and the mentee, as I will show on the next slide. So these figures show snippets from mode 2 where the hand gestures were preferred to the augmented tools of the mode 3. In the top figure, which was for mode 2, step 1, usage of hand gesture, usage of hand gestures demonstrated the scooping needle motion in a much better way than the AR augmented tooltips. In mode 2, the mentor was easily able to demonstrate the motion required to pull the two needles apart, and this was much easier to be done in mode 2 when physical hand gestures were needed instead of augmented hand gestures. This is the part where mode 3 was preferred over mode 2, and as you can see from the table, mode 3 was preferred over mode 2 in steps 2 and 5. In the interest of time, I will not go in detail on those. So in conclusion, our study demonstrated the feasibility of skill transfer, and it showed a better performance than mode 1 and equivalent performance to mode 2 for this particular step of intracorporeal suturing. Using realistic dynamic visual-based cues, it was able to facilitate effective communication, and because there were no interruptions through tool handover and no large setups were required at the remote site, it was considered to be practically more feasible than mode 2. The limitations for this particular setup, as you might have noticed from the video, was there were ambiguity of certain words used in the instruction, such as this, that, and there was obstruction of the tools on the mentee screen when the mentor forgot to move them after the demonstration. To conclude, there are certain limitations of our study. There needs to be an increase in sample size and additional subjects to confirm the feasibility of this prototype to other surgical steps other than the laparoscopic intracorporeal suturing. Also, our study doesn't focus on achieving competency of skill, rather it focuses on evaluating if there is a knowledge transfer between the mentor and the mentee. But for future directions, our team is doing some projects based on the automated transparency of the augmented tools to avoid obstruction. We are trying to do additional studies to measure the learning curve for skill acquisition. We are also trying to compare the advantages of the augmented instruments versus the augmented hand gestures, which have been published in recent literature, and to see if one is better than the other. We are thinking of using this instead of laparoscopically on open surgeries using microscope HoloLens as a head-mounted display to display the mentor's tool motion. And finally, we could also fuse preoperative image data to provide guidance contours for the different instruments. Just to finally conclude, the system facilitates the remote transfer of surgical skills and can potentially aid telesimulation programs, leading to a well-rounded surgical training curriculum. Thank you. Questions?
Yes?
Thank you very much. The issue of learning from laparoscopy is quite popular for some reason. Presumably it is a challenging surgery. But the way you have shown in the videos looks relevant to the advances of microsurgery. Have you checked advances from there, because there one has to use the devices, but the devices that one has in their hands are not touching the body. There are other devices touching the body. Is there some relevance in that?
Yeah, so you're talking about robotic surgery where they use the Da Vinci system as an
No, it's not a robot that does the surgery. These are the humans that do the surgery, but they don't hold the two devices. I don't know how they are called. And they hold some surrogates, and the devices that go to the body are much smaller, and therefore can do other movements.
No, we haven't looked into this. We have looked into, I'm sure you might be aware of the Da Vinci surgical system, where the surgeon is on a separate console. We have looked into those because those instruments have a higher degree of freedom, but we haven't looked into the microsurgery. So that's an interesting point, and possibly we could look into that.
Okay, thank you. I'm asking for the next presentation. Thank you.
Thank you.
The next paper has the title Secure and Modular Sensor Network for an Ambient Assisted Living Field Study. That will be presented by
Simon Goman.
Simon Goman. I think I say almost right.
Close enough.
You have 50 minutes to +3 for questions.
Hello and welcome. Thank you everybody for joining my presentation about our secure and modular sensor network for an ambient assisted living field study. My name is Simon Urman. I wrote this paper together with my colleagues Stefan Kunze and Alexander Weinberger from our Deggendorf Institute of Technology. And down here you can find more details on our website. It's also in the end again. For some reason. Okay, so let's jump in. The agenda. First of all, I will present the project itself, then the requirements, the technical ones, as well as the project requirements, our system architecture to meet these requirements, and then our balancing act of privacy and anonymization, and in the end, the conclusion and learnings we had during our field study. Here I want to mention this presentation will not be about the results or the reasons why our healthcare scientists chose certain sensors or wanted to measure certain data. This is a rather technical presentation, but I hope everyone can follow. Okay, so first of all, the project Dein Haus 4.0, or in English, Your Home 4.0, live longer at home. The goal of the project is to use sensors and devices to allow elderly people to live longer and independently from others in their homes. Among other parts, the biggest part of the project was the field study. For the field study, we collected medical and housing data to find correlations in the data and identify risking factors to find the risks before the incidents happen. For the field study, we had 76 participants living in 68 households, and yes, we had 8 couples. We recorded the data for up to 6 months, depending on the group they were in, and it was located in the district of Lower Bavaria. You can see marked red in the map of Germany, close to the Czech and Austrian border. Okay, first of all, the overall or general requirements for such an architecture. Our project was located in the so-called ambient assisted living. This is just the term for combining smart home with medical or healthcare data or sensors. So the first important group, the literature found, and the first group is the modularity, that simply said just makes sure that everything fits together. There's not one standard to combine all sensors and all software to work together, so this is very important. And also keep in mind the maintainability. We have usually not so keen people on tech, or we have people that somehow can't help so good. So usually it will fall back to us to fix stuff on site. The second group is the availability of services. This is the kind of technical perspective of ambient assisted living. The idea is, of course, scalability is important. You don't want to have a completely new architecture. Just if you increase the number from 100 to 1,000 people. And also, as everyone can think, reliability and efficiency is very important. If you open a website and it's just not available or it loads for ages, this is not so nice behavior. The third group is the services delivery. This is the kind of real-world perspective. So, for example, the scalability due to the number of seniors means if you think about food delivery, it makes a huge difference if you have to deliver 100 packets or 1,000 packets to seniors. And also from the perspective of the participants, security and privacy are very important, especially for this kind of field, because we have medical data. These are the most sensitive data we can measure. And the last part, the adaptability, just means we should design a system that meets the requirements of the elders and not design something for our needs. For example, if you think of an app, it could be very fancy and fancy colors, but it is important to have high contrast and large fonts so the elders can read it. Okay, and now let's come to our project requirements. These are the requirements we, the technicians, come up with our healthcare scientists. And these are not complete, of course, but these are the relevant ones for our architecture. So first of all, the first requirement is data shall be stored centrally at Deggendorf Institute of Technology to make it easy to analyze the data from our scientists. The second requirement is analysis of a single participant's data shall be possible. Make some of the best practices impossible. The third requirement is no identifiable data shall leave the home. So all data transmitted over the internet shall be anonymized. And the last requirement is the data shall be visualized on the participant's tablet to make it possible for the participants to see their own data. They measure the medical data and the housing data. And of course, some more, but these are the relevant ones. So if you quickly think about this, you come up, it's not so trivial to design an architecture to meet all these requirements, especially, as I said, some best practices are not possible with it. So let's jump into our architecture. For our field study, each home, like one home, was equipped with 10 sensors, and this is the list. And each participant got his or her own set of medical devices. For the medical devices, we had the issue, we wanted medical grade quality of data. So the open solutions, like in the initial phase, we wanted to have, or wanted to avoid cloud, but if we want medical grade, there is no manufacturer that says we have open source. So in the end, we ended up with things, and each participant got these 3 devices. If we have a home, then there were 10 sensors, and for 2 people living in the home, 6 devices, 3 per participant. And of course, we gave each home a router to access the internet. If they already had internet, we used a Wi-Fi router just to make it easy to have static IPs. Or if they did not have internet yet, they got a LTE router. Each participant got a tablet to view their own data, and our central brain in the home was the Raspberry Pi, a so-called mini PC. This is the architecture we designed, therefore. So first of all, we need a database to store the data centrally. And then our kind of first issue. And the medical devices have built-in Wi-Fi, but as I said, they transmit the data directly to the cloud. So to get this medical data somehow into our central database, we use the REST APIs. Withings has very good development APIs, so we regularly copied all the data in the Withings cloud to our own database, but it is not possible to tell Withings initially to send it to another location like our database directly. So we had to take this step over the cloud. Next is our smart home, kind of smart home architecture. This was completely designed from ours. So first of all, we had the 10 sensors you saw earlier. For the transmission from the sensors to the Raspberry Pi, we used the Z-Wave protocol. It is very bandwidth efficient, so it takes very less power, and hopefully the batteries would last long enough, and it has also a very good range, and it allows encryption. Then we have the data on the Raspberry Pi. There we had a local InfluxDB database to also cache the data locally in the home, and then transmit the data from the Raspberry Pi to our local or central database via the MQTT protocol. MQTT is a IoT protocol based on TCP/IP. It is also very efficient. It has low overhead, and the neat feature of it, it allows to transmit data without data loss. It has built-in caching with the so-called quality of services, and with this you can configure that or assure that there's no data lost during the transmission. Also, we used a VPN tunnel to have a secure connection from each home, from the Raspberry Pi in each home, to our Degloff Institute. Okay, now we have all the data in our central database. To allow the participants to view the data, we are using this InfluxDB that is located on the Raspberry Pi. So we did not make direct requests to the database, but what is in the home should stay in the home. We developed one app, our Deinhaus 4.0 app, that visualizes the data from the home, and we just use the proprietary Withings app for the Withings medical devices. And for support, we just used a simple SSH connection to each home to identify issues like devices were down or something, and on the other hand also updating all the services running. We decided for a simple solution, like we could use Ansible if someone knows this, for example, but we decided actively for the simplicity of SSH, because in the end we would have to make on-site appointments anyway. Okay, this is the architecture, and now let's jump into our balancing act of privacy and information. If any one of you has worked with data, then, and also we heard it in the morning with the very good talks, if the more anonymization you add, the less data quality you will have. So as one of our requirements in the project was, we want to analyze the data of one participant. For us, it was simply not possible to use k-anonymization or other best practices. So in the end, we used the so-called irreversible anonymized data. And now I will present you our way we implemented this. So generally speaking, we have two types of data of our participants. We have identifying data, like the contact information, address, name, phone number. And on the other hand, we have all the data we are collecting, the sensor data, the medical data. And all this data is transmitted to the database. So we decided every home and every participant's data got a random ID. This is shown here, and these IDs were not the same. So each home has its own ID, and a different random generated ID was used for the contacts. Also during the transmission, MQTT allowed, based on a topic selection, to filter certain topics out, like metadata that would make it again possible to identify directly. And yeah, that's it. And we did the same, or we had some issues doing the same with the Withings devices, because it was like, it targets the end user and was kind of not intended way to use it anonymously. So we used this workaround to use the random ID as their second name. And for the algorithms, Withings uses to calculate some measures, for example, the heart blood velocity. It was important to use the real birth date, at least the age, and we defaulted it to the 1st of January of the year. And then, if we had on-site appointments that were required, only our project leaders had this matching table to allow, if we identify the house with the ID 1234 has an issue, and we need to go there, then we somehow need to get the address of it. And so we had a matching table that was really printed analog, not in a database stored or anything, and only our project leads had this central matching table, and that matches only the IDs and from their home to the real contact information. And then this allowed to have our on-site technicians to only know the contact information and know, like, replace this sensor, replace this device, this and this is broken. And on the other hand, our scientists worked only on anonymized data. Okay, then let's come to our conclusions. We noticed that our central point of failure is the Raspberry Pi. The MQTT protocol has very good caching, there were no data loss, but the sensors, if our other side of the sensor was not available, it just sent it into the abyss and this measured data was lost. We had by design a slow response time on site appointments because we always had to ask our project leads. We noticed that some Withings devices logged out due to the inactivity, and then we again had to do on-site appointments to log them in. The acoustic low battery alarm of some safety sensors like the smoke detector caused anxiety due to some participants because we thought the batteries would last long enough. Obviously they didn't. And one learning from developing the app, if you develop a progressive web app and it is served via HTTPS, make sure all sources are served via HTTPS, so secured, just for the software engineers. And some way more issues nobody thought about that might occur. So down here, you can find us on the website, which we have for now 4 different types of Dynehouse projects. Our site is the Dynehouse 4-0. The others are also associated with us, but they are not us. And some hard facts. During this field study, we collected 5 million medical data sets and 21 million IoT sensors. That's it. Thank you very much. And now it's time for questions.
Any questions? Yes.
Was random name you use is a static name, or is it changed automatically every 10 minutes by a script in the local computer? Which name do you mean? Where you showed some task where you can set
this one.
Is it static or
This
change it every few minutes by a...
No, this was static. This was the same name as for the home ID.
To make it more secure, doesn't it make sense to automatically change it by a script?
Yes, but the point with Withings was this is all proprietary. So we had really less way to optimize or anything. So it was this real balancing act. We also didn't want to use the cloud at all, but we wanted to have medical grade data. And we couldn't just find like devices that were targeted for the end user that made this
simple with a good data quality. So these medical devices were really a tough task in designing this architecture. And yeah, just for simplicity, we use the same, but it is not intended because actually this is the name, and we would have to log into each account of these devices and change the name ourselves, like there's not intended there's an API or something. So this was just not practical, but of course it is a very good idea to change the names and all the identifiers regularly, but this was not so easy.
I was a little surprised by what you have said about privacy considerations. I made a picture, but I think we should not take back on it now. Did you make a survey among the elderly people, and they anonymously said that they do not want their data to leave the house? The reason I'm asking is that if you ask among the young people whether they want to be monitored all the time, they are not going to like it. But if for an old person the decision is between going to to a house for old people and staying at home, then the privacy issue takes another dimension. So did you consider, which age group were you considering? Were you considering people who wanted to stay home and were worried that they would not be able to do so?
Exactly. So the answer to the first question is these were all decisions made by the health scientists, and also they made like the real investigations with this formal paper stuff. So I'm only a technician, and so I'm not that much involved. What I can say, all the participants were, I think, 65 or older, and they were for the participation in the study. They also got videos to live more actively. So some diseases were also sorted out because they should also be able to participate in this other stuff. But my presentation was only about the technical part. You can read about this in our paper. And the other question was, and yes, this was the concern, to be better monitored, but nevertheless we had to, as we were doing healthcare science, we must meet an ethical contract, and so this is why we had all these considerations.
Well, we have one more question, but we are out of time. Can you make it in the coffee break, or you can make it like 30 seconds? Quick question.
No, thank you. I have another question, but only one of it. So what, for the selection of the sensor for the project, what methodology did you follow to say that, okay, we need these readings, RWBP or
These requirements were all made by our healthcare scientists. Like I said, I'm a technician. I don't know the reasons why they wanted to select them. And our point was then on the other side, which sensors can be used to measure. Also, the sensors listed are multi-sensors, so nearly each or all sensors measure also temperature, for example. So, but these were the minimum requirements made by our healthcare scientists for the field study.
Well, now we'll have the next paper, that is hemoglobin estimation from smartphone-based photoplethysmography with small data that will be presented by Diego Silva. This name I can say.
And one short hint, if you're interested in for the reasons, I can give you the contact, and you find it also on our website. So.
While Diego is preparing the stuff, I have some questions that I want to make you in the coffee break.
Okay. So I think I have everything.
Sorry about that. So, what we were.
Okay, so hello everyone. I'm Diego from University of São Paulo. This paper was made with some colleagues from the same university and also people from the hospital of the Federal University of São Carlos in Brazil. Okay, so the photoplethysmography is something like this. This is something that we are using right now, the fingertip oximeter. And after all, this is a time series, so this is what I'm talking about today, time series, okay. But the main motivation for our project is mainly this phrase here by the World Health Organization, that digital technologies such as mobile wireless technologies have the potential to revolutionize how populations interact with national health services. And I think this guy here is not there in that phrase, but this guy here is. Because the cell phones are more popular and widespread, so we are trying to simulate some photoplethysmography, I'll say just PPG, using the cell phone camera. But this raises a lot of questions, and I'm addressing some of them here in this paper that I'll talk better later. So we are collecting some data, and this is the procedure, okay? We have the invasive blood test, and then we have this PPG using the cell phone. Then, of course, merging them, we have the labeled data sets to perform the tests I'll show you. Using this, we can have a lot of parameters like hemoglobin, glucose, oxygen saturation, etc. If we use some other exams, we have, for instance, blood pressure. But in this paper, I'll focus on hemoglobin because, for many reasons, like oxygen saturation is too easy, and this kind of stuff. Okay? And bilirubin, we don't have it always, and other things. Okay, there are some papers related to this, people using different IoT and cell phone to gathering data. So the first question is why collecting new data? The main reason is because all the papers, or most of them, we can put them, those two groups, are specialized hardware, which is okay. It's very nice to research on that, but it's for the future maybe. And also, if we're using cell phone, we usually assume that we have control light, like a specific source of light or chambers or something like that. We are talking about the cell phone and that's it, independent of the light, okay? So the data set that I'm using here, it's a bit limited because we had the pandemic and the data was collected during the pandemic, so we had some restrictions, and also patients were refusing to participate and some other problems, okay? So in 1 year, we got 63 patients. That was hard to us. So some questions. What if this is the real scenario? It's really that hard to gather data. There's a mistake here. So if this is the scenario, what can I do with this? Okay. First of all, we are considering some different deep learning architectures. They're there, the multi-layer perceptron, fully convolutional network, and ResNet. They're proposed for classification. We just modify a little bit for regression because we're trying to predict the hemoglobin. We tried some traditional algorithms, traditional not deep learning, and they did not perform well, so we keep using deep learning. Okay. And then we tried some techniques to deal with small data because we think 63 patients maybe is too small. But the spoiler here is everything that I show you here, we already tested with larger data sets and they all keep doing the same effects, okay, having the same effects. So the first one, first thing, we'll have 30 seconds signals, and then we divided them in 5 randomly selected windows of 5 seconds. So like this. They may have intersections and etc. Okay. There's one problem here that sometimes we have some artifacts in the signal. That's the main reason for small windows. And if you're randomly selecting, so this guy will appear sometimes. Okay. So we also have some cleaning. Specifically this one, that's one medoid we call it. We measure the distance between all the pairs of windows, and then we get the one with the smallest average distance to the others. And we also use a data augmentation. We applied some warping, some noise, and some random dropout in the data, okay? And I don't have many time to explain it better, but I prefer to discuss the results here. First of all, if you see the full signal setup here, we see that we have a mean average error, in the best case, 1.75. This is too high, okay? Our goal is going to 1 or less than 1. All the techniques we applied improved those results, but the best we could do with 60 patients and these architectures was this. So using windowing, not cleaning it and augmenting the data is the best scenario for us, and then we have 1.5 or something, okay? And not the cases, augmenting with a window was the best way to go. But one interesting thing is here. This is the full scenario, and then we use the augmented data window, and etc. And we got this. The main point is we reduce significantly those outliers here, okay? Those are the most dangerous, let's say, results, okay? This means that the augmentation is doing its job, because once we are adding variance to the data, we are reducing the variance of the model, okay? This is the expected for machine learning, and it's happening, so that's good news. And, okay, I had a bit more discussion, but I forgot to... Okay, so we have a lot of questions open yet. First of all, we are collecting more data. We already gathered at 200 or something new patients, and this is still true, but the numbers are a bit lower. So yes, we need more data, probably much more. We are trying better architectures for whom works with time series. Just one example, inception time, which is bigger. We are trying to do some classification instead of regression, and also multitask, like instead of predicting the hemoglobin level, we are saying, okay, this guy is healthy or unhealthy, so there's the range, okay? Also other parameters, like I said, blood pressure, bilirubin, in specialized models and multitask models, and decomposing the time series and using a multimodality, like taking photos from the palpebral conjunctive may give us some information for bilirubin and other parameters. So I have one invitation here that feel comfortable to contact me, because this go from our 5 years or something. I have a big project in this, and if you're interested in collaboration, we are open to it. Okay, so I think that's it. Was quick. Thank you. Yeah, like 8 minutes or less than this.
Any question? Yes?
Yeah.
Hi, thank you very much for your presentation. I also work in the field of imaging, more especially reflective imaging and
Okay.
imaging. I was a little bit surprised that you mentioned that oxygen saturation is easy to calculate with reflective imaging.
It was for us, I don't know. But,
the thing is, most of the literature papers show that there's a patient dependency in the
yes.
calibration curves due to the penetration depth.
Yeah.
Also because there are some factors that affect the PDG signal, like the pressure. So I was wondering if you had, if this trending that you see might be due to these pressure changes, and also how you could correct this penetration depth, especially in the ranking region. So
I'm not sure about the penetration, but First of all, I'm sorry, that's not exactly easy because what we did is, first, there's one thing about our data. It was easy because nobody was with oxygen level really low or something, so maybe there's a bias in the data, okay? But this thing is related to the pressure. It happens a lot on the end of the signal because of the flashlight. It hits the finger and then people move, you know. And if I use those windows to predict, the results are bad for anything that we try, including oxygen levels. Okay, but I don't know exactly the penetration. I have a colleague in the medicine school. He is always talking about this, but I don't know exactly what he's talking about. But yeah, this is in our zone to understand it better.
Thank you very much. I will follow your work.
Yeah, thank you. Yes?
Yes, so thank you for the presentation. I just have two questions.
Mm-hmm.
You work directly on the raw signal without any pre-processing, any filtering, any...
We're just normalizing it. This guy is between 0 and 1. We tried to normalize it each window, but it's the same than doing this.
How do you do, what did you do with overlapping results?
Okay, it's not a problem for us exactly. Just one important thing I forgot to say. Our results here, we use the tenfold cross-validation, but we are ensuring that one patient is just in the training or just in the test. So the intersections are not exactly a problem. And we don't know how to select windows not randomly, you know. That's why we try to clean the data because we thought that, okay, if you're getting this thing, this is too dirty, so let's put it off. But it's not good actually. Maybe because in the test set I have this as well, so let that in the training.
Have you considered the patient diversity in data set collection?
Excuse me?
Patient diversity, like age.
Oh yes, we have those data, age, sex. We also have self-declaration, skin color. We did some analysis, but when we separated groups, we didn't see significant changes regarding this. I don't know if this is your question.
Yeah, but recent studies have shown that the colors are impacting the DBG as well.
Actually, no. We had one case that affected a guy, a builder. He was with the hand a bit dirty, and the signal was almost flat. But the skin color was not a problem. Actually, we are using the three. I didn't say that because I prefer the questions than the presentation. We are using the red, the RGB, the red, green, and blue channels. This is on the red, okay? But I don't know why, we don't know why. Some people have really, the green channel is really important, and for other people it's not. We didn't see any relation to anything in the blood test, anything in the skin color or something. There's some stuff that we still don't know. I think there was another hand.
Yes, thank you for the presentation. Just one question that for my point of view is crucial. For collecting the target fiber, in the hemoglobin, as it happens in pressure measurements for calibrating models for estimation PPG, sometimes we sample one target value using, for instance, CAF. Okay.
not sure if I completely understood, but yes, you have a good point that mapping a long time series in one value is really complicated. This is one of the motivations for window in small chunks, but also trying to avoid some artifacts like this. So we are trying to remove some noise. But I'm not sure. We didn't go further. Maybe just one important thing: the deep learning algorithms we tried, they're this good for long-time series, and the other guys that are not deep learning based, they were much worse. But we didn't try the other guys in the window signals. And now you made me think that we should, because they suffer more than deep learning to map the long-time series in one value. So probably this is something that we need to investigate better.
Because the thing that you use, so my question is, how many points did you acquire of PPG, since I suppose that you have a lot of parses that have to map in one value.
Yeah.
And so I would like to understand the measure, since I think that you use asynchronous systems.
Yeah.
My point is, how many PPG values you record within the sampling of one target value?
How many points you mean?
Yes. How many PPG cycles, let's say?
Yeah, it's 30 seconds. I think you're collecting in 300 per second.
Okay.
Yeah.
Well, it is a nice discussion, but we need to move forward.
Okay.
Sorry.
Thank you. Thank you very much.
The next paper and the last one of the session has the title of Predicting Patient-Based Time-Dependent Mobile Health Data, that is presented by
Anna Kleiner.
Sorry for my spelling.
Okay, so welcome to my presentation about predicting patient-based time-dependent mobile health data. I'm Anna Kleiner, and I have to see how I get to the next slide. Yes, I can touch. Great. So first of all, what is this project about? This project is started as part of the Unity project. The Unity project tries to find the optimal treatment for tinnitus, where tinnitus is the phantom perception of sound. And this is important because there's not one tinnitus treatment that's best for all patients, but the treatment depends on characteristics of the patient. And one part of that project was the collection of data of the patients on each day through a mobile app. So there were daily questionnaires measuring the current symptoms. And this data means that we have patient-based data, so data for each patient. That is time-dependent and collected via mobile health, which is why this paper is called what it's called. So the data that we have is based on questions rating the loudness of the tinnitus, the stress, or the jaw tension, and tinnitus distress as the ultimate variable that we want to predict. And we have over 400 users and over 30,000 entries. Here you can see, for example, time series of the tinnitus distress, where you can see that we have very different time series depending on the patient, and also different amounts of data. So some where we have really few data and some with a lot of data. So this creates the research questions that we ask ourselves is, can we predict the data of one patient? So for each patient, can we predict that patient's next data entries? And this is divided into 3 questions. First of all, how should we decide how much of the past data should be exploited? Then, to what extent do we augment with data of similar patients, because we have all the data of other patients? And lastly, how do we evaluate our models? All on our case study here of predicting tinnitus distress. But the approach should be general. So first research question, how should we decide how much of the past data should be exploited? For this, we have basically 2 questions. First of all, should the model be time aware?
So are there any autocorrelations in the data, which I will expand on in a minute, and correlations with weekdays, holidays, or seasons, because then we need time-aware models opposed to not time-aware models. And the second question is which predictor variables should be used. So are there linear correlations? Are there non-linear correlations? And do they differ between the patients? Because then we need to use feature selection algorithms or other ways to create models depending on each patient. So first of all, on our case study of tinnitus, time-aware. So if the model should be time-aware, we looked at autocorrelation functions, which basically look at the correlation with previous days. So for example, a lag of 7 would mean correlations with 7 days prior. And as you can see here, we don't just have data of one patient for each day, but we have data of all those patients, and we don't want to create one model manually for each patient. So we analyzed all data together and now we have distributions. So for a lag of 7 days, so correlations with 7 days in the past, we now have a distribution of all the autocorrelations of all the patients, which is displayed here as box plots. But as you can see, autocorrelations in this case were quite small because the blue dotted borders are the significance levels of 0.2, and already very, very fast all box plots are within that border with just some outliers above, which means that in our case we do not need time-aware models, as we do not have correlations with the past data of the patients, and also no correlations with weekdays or seasons, which we found out in similar experiments. So then we looked at, okay, if we can't predict the data of one patient from the past days, can we predict it from the other collected answers to the questions? So we looked at correlations, and again we had the point that we had all those over 400 patients and didn't want to create manual analysis of each patient. So we used parallel coordinates, as you can see here. This displays the correlation with each of the other measured symptoms, so for example the emotion or the loudness, and has one line per patient showing the correlation strength. So what you can see here, for example, is that for emotion, for a lot of people, emotion correlated negatively with tinnitus distress, but in varying degrees, and for some it correlated positively. And loudness, for example, correlated very positively for a lot of people, but also with exceptions. So as you can see here, correlations were quite different for the different people, and this is why we then needed feature selection approaches that select the correct features for each individual patient. So then, to what extent should we augment with data of similar patients? The general approach here is first, do we actually need to do that? This is required when either we have patients with low amounts of data or when overfitting is a problem. And if we do that, then we have to decide on the similarity measures, which I will expand in a minute. Also which patients are considered as possible neighbors, because comparing each patient with each other patient has a huge computational complexity. And lastly, which neighborhood size should be selected. So for example, a threshold or just like a basic number like 5. So similarity measures. We collected some different similarity measures that could be chosen. Static similarity is the one that's used most often, which is basically just using static data of the patient. So for example, their age or gender or medical data. But as we have all that time series data, it is of course also interesting to look at time series similarity. For example, just measuring with Euclidean distance, the distance between the time series, or using the dynamic time window approach. Another approach that is used sometimes is model similarity, so training one model on each patient and then measuring the similarity between the model parameters. And the last two I will explain in our case study, because since our data did not have any autocorrelations, we treated the data entries as independent of time. So instead of like having all those entries that follow on the time axis, we just treated them as one set of data entries without any order. So now we have for each patient one set of data entries, and now we need similarity measures for that. Because like how do we measure the similarity between two sets of data entries. And we chose here an approach that is inspired by agglomerative hierarchical clustering, which is a clustering approach that merges two similar clusters. So we used that approach because if we calculate the similarity between two clusters, we can use their approach of measuring similarity between clusters. And this is based on, first of all, defining the similarity between two data entries, so one data entry of one patient and one of the other, where we use basically just Euclidean or cosine distance on those vectors. And then, depending on the specific approach, of all the possible pairs of data entries of one patient and the other, one is selected as the final distance of the two clusters. So for single linkage, we just choose as the distance between the two clusters the smallest distance. For complete linkage, we use the biggest distance. For average, we use the mean of all the distances. And for centroid linkage, we compute the centroid of each cluster and then measure their distance. So this were the vector set distances. And the other thing that we looked at is correlation strength. So if I can remind you of that parallel coordinates plot that I showed in the beginning, here we can also just see if maybe patients who have similar correlations are similar and should be trained together or are a good neighborhood. So again, we use Euclidean or cosine distance to basically compute the similarity between those vectors of correlations. So basically this would be if two lines are similar here. So how do we evaluate our models? So the two approaches here are expert review or comparison with baseline models. And afterwards, there can be a further evaluation with the best neighborhood model on the level of the individual patient, which I will also explain on in a minute. And the baselines that we used were first of all a baseline personalized, so this does not use any data of other patients. Baseline global, which is trained on all available data and is just the same for each patient. And baseline random, which is used to compare distance functions and is trained on a randomly selected neighborhood. So our results. As you can see here, our results are quite similar for all the models. The only one that has a higher value is of median MSE is the personalized baseline model. We are using the median MSE here because, again, we have one model per patient, so we have a distribution of the mean squared MSE. And as we don't want outliers impacting our results, we just use the median instead. So as all our models have quite similar MSEs, we looked and just as all our models have quite similar MSEs, we compared still the best model with Euclidean single, which is a bit better than the rest with the baseline models, just to see what the reasons are for that and if we could still draw some conclusions. And the first thing that we see here is if that best model, Euclidean single, so Euclidean distance with single linkage, actually performs better in 63% than the personalized model, but also in just about over 50% than the other two baseline models, which means that for a lot of patients, actually the baseline model is better than the personalized, the neighborhood model. And this is interesting because this could mean that for some patients we should use a general model and for some patients we should use a neighborhood model. Or the second question that we ask is, okay, if there's that difference, if the model is better for some and whereas for others, maybe that's just some random fluctuations. How big is the difference actually in MSE? And if we look at that, what the difference is? This is supposed to work. Okay. The difference between the MSE of the baseline model and the MSE of the neighborhood model, we again see that the difference is quite small actually, apart from the personalized model. Actually, for the personalized model, what you can't see here, we actually realized that for patients who have really small amounts of data, the neighborhood model was way better than just using their small amounts of data. So Discussing these results, we see that first of all, using Euclidean distance and single linkage performed best. Euclidean distance performed better means probably that the magnitudes of a feature vector are important for similarity. So patients who have very, very high values for loudness, for example, should be clustered with other patients who have also very high values of loudness. And single linkage is probably better than the other linkage methods because it's not very sensitive to outliers because it just uses the smallest distance. However, the differences between the best model and baselines are small, which means we have a high need for better neighborhood functions, but they are still better than the just personalized model, so it is a good approach to actually use data of other patients. And when analyzing the best performing models, we saw that the neighborhood model was only better for a subset of patients, which could mean that there may be approaches that just select the best model for each use case. So, completing my talk, first of all, I presented an approach to build personalized predictor models for patient-based time-dependent mobile health data on our case study of predicting tinnitus distress, and I hope you got some ideas from that approach for further approaches. And second of all, we realized that neighborhood models might improve performance, but they also strongly depend on the chosen distance functions and the chosen neighborhood. So there's definitely further research needed on how to choose a good neighborhood on such data. Yeah, with that I want to thank you for listening, and if you have any questions, I'm happy to help you.
Any questions? No questions? I have one question. If you have these results and you say that the best performance against the baselines were not similar, but the difference was not so big, what do you think is necessary to increase this distance? What is the next things that you or someone should try to may improve or may affect these results, in your opinion?
Yeah, better neighborhood similarity measures, basically, or maybe playing around with choosing a smaller group of patients as neighborhood, but basically finding better similarity measures that, because the ones that we tried out did not improve results that much, and yeah, there's basically a good place for creativity and finding new solutions.
Yes?
Thank you very much, Tom. I am not very familiar with these kinds of similarity-based predictors. And I know that, for example, feature interaction and collinearity between features is very important when you're trying to do regression models. I was wondering if in this kind of model that you're developing, that plays a role at all, because I saw that some features might theoretically have some relationship to other features that you're also using.
Yeah, definitely. We had a lot of collinearity, so we used feature selection approaches because of that to select features that are independent of each other.
And creating new features based on interactions between the features that are collinearly related?
No, we didn't create new features, we just used the existing ones, because that would also be interesting, but again, as we use multiple patients, we would then have to see, with our approach, we could really choose features and where the collinearity of that specific patient was high or low. And if you create new features, you have to see how that interacts with this neighborhoods and the other patients.
Any more questions? Thank you for your presentation. I would like to thank everyone, the 4 presentations that we have here, and everyone that was here to the end. And now we have a coffee break, so see you soon.
We are taking time. And we now have 5 talks, and Yeah, you have the floor. So before I would be 15 minutes per person, and I would be working at 5 minutes before that, but please do also leave at my level. I've got to remark that there have been problems now and then with this prepared sense.
Yeah, it's already done. Okay, can start? Yes, so hi everyone. It's a pleasure to be here for you guys. I'm Arlindo Galvão. I'm not the first author, neither the second. I'm the last author, so I'm here just representing my master and PhD students. And our work is entitled like Life Work Forecasting in Brazilian Health Regions with 3 base machine learning models. Okay, so in 2019, the World Health Organization come with this not a quite good news about 810 women die every day from preventable causes related to pregnancy or childbirth. So I will repeat the preventable. So we have the technology, the knowledge, or everything to prevent the death, but until that, they die. And earlier, when the United Nations tried to warn us to some goals, some sustainable development goals, to aiming to reduce the global maternal mortality rate less than 70 per 100K live births by 2030, so 2030. But in Brazil, you have a quite difficult reality. There we are much more than that, so 107 per 100K live births. Because Brazil, it's a huge country, you have different realities. Some states of there have a lot of water, and other it's completely dry. You have some good quality of public health in southeast, but in northeast are poor and don't have the same scenario. So unfortunately, you have a huge different realities in Brazil. I'm accustomed to say just we have 5 different countries inside the same country in Brazil. So yeah, until that problem that we are trying to resolve, not only to get better models or try to expand the state of art, but to try to help the country with new and better public health politicians. So we have politicians to try to do that, and they try with our Ministry of Health to implement this kind of program that use machine learning, use technology to forecast live births, so they can arrange everything that will work and prevent a lot of death. So if you have a model that can predict or forecast, here we tried 3 different novel models for all micro-regions of Brazil. So that was a tough work, because that 3 models are 3 gradient boosting decision trees, the Microsoft Light GBM, the other one it's open source, the XG boost and cat boost. And as a baseline, we compare with AltaRima and linear regression that most of all state of art using them. And evaluative mean average error and mean average percentage error. So yeah, this is the size of Brazil. Each of parts that separate are divided by our Ministry of Health. So all of these pieces is one of 450 micro-regions in Brazil. And we did 450 predictions of each macro-region in Brazil to try to help to prevent not only death, but prepare the public policies for that. For example, to put more physicians, more nurses, more multi-professional or multimodal professionals on on that hospitals, on that cities, on that micro-regions to get ready from that number of births. So the data set, it consists in a multivariable model, so it's 17 variables from that 450 microregions, and it's divided by monthly live birth, so we predict by monthly that 2000 through 2012, so 20 years of data sets we used. And that are the features or the variables that we use. So we have number of live births, health regions, and male condom distribution, female condom distribution, contraceptive pill. So all this data that we have and we arrange it and processing to try to predict everything with all these characteristics, the live births. And the results that we have in comparison by AutoArima, XGBoost, GetBoost, LightGBM was the best results that we got. AutoArima, it's kind of similar, but LightGBM was best of that. And here are a graphical comparison of the two. The AutoArima have some difficulties to the last year because the prediction window is 2 years. So the public policies that we have may try to prepare 2 years earlier to get better or to get the program to working, to running. So that are the requisites provided by the Ministry of Health of Brazil. So here are 8 different regions, micro-regions, for example, to the north, to the south, and LightGBM, of course, is the best model in that result, in our results, but he have a hard time dealing with low population regions because we have a huge and really little micro-regions in Brazil, and we have a different scenarios over there that they didn't have some specialty or some hospitals, and they use the hospital of the neighborhood area to try to get this effort. So LightGBM was quite good, but they have some really bad results when we have a low population regions. So yeah, the conclusion that we have is that the best result, of course, is LightGBM. With mean absolute percentage error of 0.07 and mean absolute error of 39. And remembering that's not so good with low population regions. And as future work, we are trying to get, of course, 2021 until now. We already have some data set that we are working right now, and it was worse than ever because they take the entire window of pandemics. And in Brazil, it was almost 700 people died of COVID. So it was a completely disaster for moms or for not live births. And of course, we have to test new models and new variables too. But yes, of course, these are our results for here, for the benchmark, to try to get another one. But this is our main goal. This is my state that I live. This is the prediction that we can give for the government, we can give for our Minister of Health, and they can predict as this heat map, how bad is that region. So for now, 2 years, that will be worst. And for example, you see the green areas, that's not good as well. If you see up there, 35% only. You have to reach until, I think, 70 or 69%. We have a lot of homework to do, and these are the first step for my perspective that we can show not only the public systems, but they can prepare themselves, so how much nurse, how much physicians, how much psychology, how much health professor they can give and can for casting the number of how much that we can cost and put the right places, the right amount of budget, and then we have more intelligent public health politicians. That's it. Thank you very much for your attention. I'm really direct of the point, and I'm here if you want some questions. My contacts and QR code. Thank you very much.
Just one last, because I see that maybe the seasonality has not just really fit to the real expected value. So do you try to reduce your evaluation, or have you also planned to use the people or some kind of recurrent evaluation? Because you have already tried ARIMA. ARIMA is just the people network without application touch. So
yeah. Yeah, exactly. So you can imagine 450 simulations, it was quite a lot. So these are our first step. We have another paper that already I presented in the morning, that we already have testing a bunch of other models, of deep learning models, of recurrence models, and all other models, but only for one state for now, and then we are spread to entire country. And other strategy that we have, that maybe we can amplify the data set, or amplify the granularity of the data set, because now we have monthly. We have some data set of daily, but it's not entire one, so we have to collapse on the average, for example, to a monthly, and then you have the monthly resolution. But maybe we can try to do, for example, daily, and maybe we get better results.
Actually, the evaluation is only based on the average error. So there's other things we can also try to check. For example, is the first 30 days is better than the last 30 days? And the trends is also one important indicator, right?
Yeah.
Trends, seasonality, and also the reality. If you can just evaluate the three different aspects, maybe you can also tell more details according to the outcome.
Yes, yes. And here we have other hyperparameters that I didn't mention, but of a lot of windowing strategy to maybe to get not only 1 month, but 2 or 6 or 7, and then we just escalate that with 3 different models. So first of all, we get January, the second February, and that will be gone. So we get a little bit better results. So yeah, of course, we have a lot of other strategies to try. Okay, thank you.
I also have a question on the results if you could go to the plot.
Yes.
No, not this plot.
Sorry.
Yeah.
This one. Yes.
Okay, these are aggregated results, but if we consider the different regions or micro regions as you mentioned, as you called them, they are presumably of populations of very different sizes. And I was wondering whether there are some individual curves which are more reliable than others, and whether we can do something with that if some are not very reliable, but there is some sort of a neighborhood or a neighboring micro-region which has more data, whether you can inform on that?
Yes, yes. Actually, we are just trying to do a strategy that will be more layers. Yeah. Then when this result is not trustable, we just get the other micro region and get that comparison, or even yes. So for now we don't there yet, because that was some requisites of the ministry. It was a direct demand, and they said, okay, these results are way better than we are using now. So and then I try to adapt to the new one based on that. But of course, it's not a real-time system. We have a lot of other departments who use this data set and this data and have their own predictions, and they elect the better results.
Okay. On what do they choose? On quality, explainability, or what?
They?
When you say they choose the best results.
Oh, okay. Yes, no, but no, and they have another methods, not machine learning based, that they use for their baseline. Yeah. But here they try to get another historical of that. Here we're not using, for example, this year. We actually don't have the data set yet. Even 2022 we don't have yet. They are already even closing the data set. So they are, of course, using the explainability with second models and try to get the best option, choosing with all the models that they try.
Okay, thank you very much.
Thank you. Thank you.
Okay, from Brazil to France, Yakini, Chuka, and the whole team, work about the ICD-10 code association within French informatics.
So my name is Yakini Chuka, and I am a PhD student in computer science in Femtoscience Technology Laboratory in France. And I'm going to present this paper, Automatic ICD-10 Code Association, a challenging task on French clinical text. In this presentation, I will start with a scientific context and the objective of this work. After, I will talk about the challenges we face in achieving ICD code association task, and then I will present the result of our experiment and conclude. So when a patient is admitted to the hospital, a record called a patient file is created. This patient file will contain, for example, reports on consultation or operation carried out by the services that the patient have visited. The medical report provided by the service can contain, for example, patient story, diagnosis, prescription, and so on. This patient file is the basis of many medical analyses, and for example, association of ICD code is one of analyses performed on this patient file. What is ICD code? ICD code is an international medical classification established by the World Health Organization to monitor and analyze the health of population. This classification contains over 140,000 procedures and disease codes. ICD-10 because in this work we consider the 10th edition of this classification. So associating ICD code consists of going through manually the patient file, analyze it, and assign the corresponding code to diagnosis, patient story, procedures, doctor's conclusion, and so on. It is a labor-intensive and time-consuming task. So the question in recent years in medical research is how to perform automatically this task. The objective of this work is to set up a system to automatically associate ICD-10 code. With a lot of machine learning application, we know today how to address this type of task. First of all, it is a multi-level classification task because we have a finite number of ICD code, and given a patient file, we have to choose in this set of codes. It's also a natural language processing task because we are manipulating textual data. What is natural language processing? With the appearance of machine learning system, the question was how to process the input, the text as input. So the question is how to transform the text into numerical values so that the machine could process them. And we started this transformation with a bag-of-word system. Briefly, in bag-of-word system, the words in a sequence are represented by 0 and 1, regardless of the word order. And with the emergence of neural network, we tried to include the context in text representation. For example, the representation of a word in a sequence depends on the representation of the previous words in the sequence. And in recent years, the introduction of attention mechanism has taken natural language processing to a whole new level, in particular with transformers model, which is today the state of the art in textual representation. This technology makes it easier and more efficient to perform natural language processing tasks. Of course, this technology we used in this work. So here is how our data set is constructed. We have the patient file that contains text documents correspond to operating report, discharge letters, external report, and clinical report. To this patient file is associated a set of code, and the patient file, the concatenated text documents with the binarized ICD code from our dataset. As I said, it is a multi-level text classification task. So a supervised learning system based on the pre-trained transformers could be the solution. It is also known as transformers fine-tuning. This common approach does not work very well for ICD-10 association because this task presents some challenges like how to deal with a long document or how to deal with a large label set. Let's see the challenges of ICD-10 association. Here is a table describing our data set. The first problem in ICD code association is that the inputs are generally the long sequences. For example, the average size of our sequences is around 800, which is above the maximum input size of transformers model. The second problem is the large number of codes. In our data set, we have 6,160 unique codes, which is not the case for usual classification tasks. The first challenge, long sequence processing. As I said, the main limit of transformers model is the maximum number of tokens it can handle per sequence. So in the literature, there are two main methods to overcome this limit. Sparse attention transformers, long format models, and hierarchical transformers. The first one, long format models, it is introduced in 2020, and it is based on local attention and global attention in order to reduce the computational complexity in the networks. So that long format model can process up to 4,096 tokens per sequence. This type of model could be the solution in our work, but unfortunately there is no French language, there is no French long format model. So for this work, we use hierarchical transformers, which is the second method to overcome the limit of transformers. Hierarchical transformers method consists in dividing the document into segments, and then we calculate the representation of each segment with pre-trained transformers layer. And finally, an aggregation method is used to obtain the global document representation. There are several aggregation methods. We have a mean pooling system. We take the average of the representation of all segments by dimension. Max pooling, we take the maximum of the representation in each dimension of the segment. And the third one, we simply stack all the segment representation into a single sequence. The second challenge, a large label set. To tackle this challenge, we use the label-aware attention mechanism. It is introduced in 2019 to overcome this challenge of large label sets. It consists briefly of integrating the labels into the document representation. It allows to capture important text fragments related to certain label. Here is the algorithm of label-aware attention mechanism. Let H the stacking representation provided by transformers layer. We compute a label-wise attention weight as follows. For example, the row I of matrix A represents the weight of the label I. And then we compute the label-specific documentation D, which is the product between the sequence representation and the weight of the label. And finally, D is used to make the prediction by computing the inner product between each row of D and the related work. Here is our global architecture. I pass it because of time. And here are our results. First, we tested several architecture combination on the code reduced into families. So we have 1,564 labels instead of 6,000. And then we experimented the two best model on all the code. Here are our results. We can see that the model without long sequence processing are worse than the model with, and also the model with long sequence processing but without label attention mechanism are less accurate than the model with label attention mechanism and long sequence processing. We also trained several methods based on the most common code. Obviously, we can see that more the label they are, less accurate the model is. And finally, I present our best model in this work with the previous work on ICD-10 code association. We clearly outperformed the last model, the last French model on ICD-10 code association. And we are not too far from the state-of-the-art English model PLM ICD. To summarize, we propose an ICD code association model that uses the latest advances in natural language processing and multi-level classification. We obtained the state-of-the-art French model for ICD code association. The main limit of this work is that we cannot publish our model because it has been trained on sensitive data. And for future work, we plan to try large language model with few shoot learning techniques to automatically associate ICD code. Thank you. Library for disease machine?
Yeah, there are standard libraries like UMLS for disease matching, like matching words to diseases or to ICD-10 code. Why did you
library to automatically associate ICD code? Automatically? Yes, yes.
Why did you decide to train models instead of just matching those words with documents?
As I said, associate automatically ICD code is consists of going through manually the patient file.
No, but you could just use that library to automatically.
Yes, manually the patient file. It's not. You have. You need the specialist in coding ICD to manually associate ICD code.
So you don't have to manually. So you have the document with words, and then you just text match from all the list of words to the patient case. So you have the patient case, and you go through each word, and you just see, is this word inside of my library of words? And then you match them.
I don't know such a library.
I should take it off the record because I suspect that we are talking about slightly different things. Yeah. But I think that if there is some kind of help, this should be considered. Further questions? I happen to have some. In the medical records, for some diseases, there are a lot of records, I don't know, asthma. And for others, there are much less. And also, there are some people, there are some diseases which many people have them, but there are hopefully rather few people who have 100 diseases. So, when you evaluated your methods, did you consider this kind of skew over there, for example, were there some trend in the sense cardiovascular diseases were easier to predict than, I don't know, epilepsy or something of the sort? And where a person had many diseases, this was more difficult than for a person who had few diseases. Did you see such things?
We use a deep learning algorithm. So the facility to predict some code than other is dependent on the data set. If disease you talk about is we have many examples of this code in our data set. It will be simple to predict this type of code.
Have you considered making a histogram where you say, okay, diseases that so often have, I don't know, an F1 score so much, and diseases which are less often have this F1 score, so that you stratify
Okay, no, but we trained several methods based on the common disease. For example, K equals 10. It is the most 10 disease in our data set. So we can see that we get better result on this type of code than other.
Okay, further questions? Okay, thank you very much. The next talk is the keynote trial on incident response teams or other upscaling operators of essential services teams.
Hello everyone, I am João Almeida and I'm here to present some guidelines about how to implement cybersecurity in operational essential services, which is something that researchers think that is the IT guys should be care of it, but this is something that everyone has some responsibility in this manner, and sometimes the IT guys need the help of researchers to do something. And what he did in this work was, okay, let's first think what is cybersecurity. This protects systems, networks, and data, especially in our cases the data, against some cyber attacks, damage or unauthorized access, that this is something that is against the law. And this is very good when the people trust in the environment they are working on. They can assess the service they expect to access. They have the data that is not kept in private, but they are protected by the organization that this is the way that should be. And the business operates correctly and is productive. This is the perfect scenario. This is good when this works this way, but the problem is when does not work in this way. So someone in the past, or a team of people in the past, tried to define this in 3 pillars. That is confidentiality, integrity, and availability. And we try to have our resources following these concepts, and we try to make sure that all the technology, people, and process are protected and, in the best case scenario, are resilient against cyber attacks. This is what will be nice is this will be the state of the art, but it's not, because there are people that attack our institutions. When we talk about a hacker, we think someone like this picture, someone in the dark room looking to a computer, but this is not true. Currently, there are companies that their job is to attack other companies, as you may notice in the news, that sometimes a university or a hospital suffers an attack. So we try to, well, protect our institution and collaborate with other institutions and try to produce some guidelines that help people that wants to follow the same path and try to be more resilient to this. In the past, when we have a problem, we could call the technical guy and they shut down the machine, they power up the machine and everything is fine. In the worst case scenario, they delete everything and install everything and everything was fine. But now this is not true, because we have lines that are operating a full time. We cannot just shut down the lines, they are fully automatically. And this is extended to ourselves. Everyone here may have something in their pocket that has a lot of information about you. And if attacker has access to this, can do something bad to you or to your account, and put your life in risk, since some of you may have a car, that some of you may have a car with some technology that can be hacked, and this can be extended to the medical field. This is a futuristic image, but I know that information and systems are currently very integrated in our hospitals. I know that some research groups are trying to do this. In my country, no institution has this technology, but as something that is very dependent on systems. So in this we try to analyze the impact of cyber threats. And although I select some of them that are not quite new, maybe they have one here, but these put the institutions down, and some of them shut down, not in the case of the hospital, but I think this university was down due to a ransomware attack. And this is involving so much that artificial intelligence can be also used to support the cybercrime. Okay, now I may scare you a bit. That was the idea, to show you the impact of not being secure. We tried to create a project. We did in collaboration with other universities, and the idea of this project was to increase the capability of computer security incident response teams, because when we think that IT guy is capable of respond to an incident, this is not true. They need to be, they need to have formation, and they need to collaborate with the medical teams and the research teams, so they can handle properly critical situations and ensure that everything is reported when something bad happens. This collaboration happened because both of institutions have what they consider operations essential services due to some departments in the institution that are very connected to the medical field. And we decided to divide this in 3 tasks or 3 stages. That is training in risk assessment. We need to identify what puts the institution in danger. How can we maintain the data, the sensitive data protected and in the same time useful for the people that has access or should have access to this data? And how can we make auditories between each other? In your case, we can verify if the University of Porto is doing the things well, and they can verify the same in your cases. So the first part is to establish how can we manage this. We have an entity here, you cannot see my, here, that will ensure that we are doing the things right. Then we split the tasks between each other, and in this case, this is important. Why? Because if we need to collaborate with more institutions, we can follow this diagram, this idea of, okay, we have these responsibilities, we need to make sure what we are doing, how we will doing, and how can we accomplish the goals. And in the first part, we establish some milestones. We want to establish the process of planning and monitoring all the activities, and this is difficult because it's not a normal project that we count with a small group of people. We need to count with everyone or in every position in the departments that are considered essential. And as you may know, everyone is very busy in these days, so having the collaboration of people to have more concerns about things that shall not be the problem is not easy. We try to keep meetings between each other and get everyone involved so they can feel that they are doing something, and that something is important and that will not put the organization in risk. We try to incorporate in these important organizations that can help us to identify problems and help us mitigate these problems. We define very detailed risk plans so we can detect, okay, if this happens, what is the probability of happening, and can we solve this, or how can we solve this? And after all of this, we need to report when something wrong happened to someone that should do something. And during this project, we define all of these guidelines. We define how we can proceed in this. And the first task in these ideas, okay, was the risk assessment that was focused on the health services. We try to analyze and incorporate everyone in the information communication technology infrastructure because the data is there, and the services that are related with this data and the people that is involved in assessing this data. We're trying to following some of the guidelines of the standards. We are not here to talk about the standards, but they exist. They are difficult to follow, so we need to have some guidance to identify the right standard to apply for each situation, and these ones help us to be compliant with the law and be compliant with the directives that are currently being applied. And this first activity was identify what can threat our institutions and how can we measure the damage of these threats. Then we did some penetration testings that was incorporating the bad guys and trying to do the same that they could do and identify how successful they could be if instead of being us was a bad guy. Why this is important doing between institutions? Because I know my institutions, sometimes I look to my services and I ignore important things, but if another look look to the same system may identify things that are important. And finally, the most important was to provide guidance to everyone, not the technical guys, but the non-technical guys, especially the medical researchers, the importance of the risks that we identified and how they could mitigate these. I can just tell you one very simple, the length of the password. Some people have a password that is 1, 2, 3, 4, 5, 6, 7. And this was a very risky situation for some of the services because they are old and they do not care about these verifications. So fill this gap analysis was important and was the last stage of the planning. As a result, to create several guidelines, several documentation methodologies to help people be more compliant, and we create guidance so people can implement this in their organizations. And we are currently in the stage of implementing all the things that we find to mitigate the issues that we found. But this is a work in progress because when we implement some of the mitigations, new ones will appear, and we need to do again this risk analysis and everything. Is like a fight between bad guys and good guys. And well, I think we are, I don't want to say that we are good, but we are trying to be good. So I hope this gives you some guidance or some help to start caring about cybersecurity. Thank you.
Made this plan, what is the ideal mix of skills that such a team should have?
Well, we created a team to help the medical teams. And we try to give formation to the medical teams. I call medical teams, but I'm saying everyone that is non-technical, that is in the essential services. And we need to do something, and when I say something, is sometimes is create phishing, propository phishing to test our teams that are non-technical, to show them the impact of doing bad things, try to give them formation, and we need to realize that they don't know about cybersecurity, they don't care about that, they are not willing to spend much time caring about that, and this is a fact that we need to accept it. So we need to give the minimum but the maximum information that we can and create a team that is technical to protect them with services, with infrastructure, with systems, and with formation and sensibilization, dissemination, put sometimes news in the university journal saying be careful of this, creating these plans of dissemination about the most common threats that are everyone is willing to click or do something.
You speak about medical teams in some institutions. The protection of the individual medical teams is shifted to a big IT facility. Are such facilities involved, or are they rather caring about security at a different level?
In this project, we were only focused in the university, but my university, Aveiro, is collaborating with a hospital in Aveiro. We aim to expand this to Aveiro. We have some collaborations. They are not so deep like this project, but they think that they are protected because they use a specific, very close environment. But I know that a medical one that wants to share exam with another medical, just send it by WhatsApp. They cannot do that.
I think one of the important risk factors is the human and not the architecture. So do you have a certain training for medical staff in mind that differs from other non-technical persons?
We have, but we have a problem that is encourage people to enroll in the training. So, but we try to disseminate this like they have this information in the email, and then we have like email explains things, phishing emails that we create just to train them without they know that I have been training. And then we have the formation that is 7 hours formation about the basic stuff, password management, phishing attacks, cyber social engineering attacks, how to manage the password, why you should use a VPN when you are not in your institution. And I can say that this formation has success because the people that enroll, at the end, they learn something. They look to the day before, okay, I did this in the past, now I know why I should not do this. And the feedback is good, but we cannot get everyone due to several reasons.
Do you have specific issues or risks that you train, especially in medical staff? Because this is like more general best practice for non-technical training?
Yeah, the medical stuff is like the non-IT guys. They make the same mistakes. But the problem is they think because they are medical, they don't care about that, and they don't need to. And this is the problem. Someone from the administrative staff, we can send an email, and they, okay, I need to be careful. The doctors just say, I don't care. The IT guy will solve it.
Okay, so useful. Okay, thank you very much. From the clinical topic context to the wider health context, custom-centric, and I think very Patricia Carolina stands the output for the topic of how the ability at least. That's a bit here to talk about high configural ecological momentary assessments. And we are set now.
Yes, you go all.
Yeah, I was reading very fast. So, then we are ready. All Carsten is presenting and the additional information didn't mention is our two German universities, Würzburg and Ulm. And we can
Okay, good afternoon everybody and welcome to my presentation. Today the pleasure is mine to present to you a highly configurable ecological momentary assessment and just-in-time adaptive intervention mobile app framework we created for application in a large German scale study for breast cancer aftercare. Okay. I'm sorry the clicker didn't work properly, but now I think it's set up correctly. So for many years now, we are developing EMA and EMI, ecological momentary assessment and intervention apps for mobile devices. In the last years, we developed and deployed numerous applications for various study scenarios. From this knowledge gained from these projects, we gained the setup for the framework at hand. So the goal here was to create a highly configurable back-end independent mobile app framework that we can utilize for any kind of study in the EMA, EMI and GTI application field. So I will briefly introduce you to the framework we created, give you the background information for the project setup and application field, and also will present to you the resulting mobile application. The mobile app framework comprises 3 different layers of configuration, a very powerful content engine, as well as back-end independence through an adapter API layer, and multiple features encapsulated in different standalone modules. The first step for setting up such a project with our framework is in close cooperation with our, for example, medical project partners. There we make them familiar with the project and how to set it up and how to use the content management system. Also, a developer sets up the basic configuration files like the app icon, the backend URLs, the app name, and basic stuff like that before deploying this app skeleton to the respective test stores, for example, the Apple test flight. Yeah, the 3 configuration layers comprise the already mentioned basic configuration layer, then the module and feature configuration layer, which is either hard-coded or loaded during runtime in the application itself. Also, the third configuration layer is the app content configuration. The available app features are primarily determined by the first and second abstraction layer in the configuration stack. The third configuration layer is responsible for the actual app and app module contents and are set up, in our case, via a powerful what you see is what you get editor in a backend. The main modules of the framework comprise our powerful content engine, several account management tools like management modules like the login, the account, CRUD operations, and so on. Also, we got push notifications and user settings and user stories which guide the user through the app. The core of the framework, as mentioned, is the powerful content engine with its data model, which is used to represent basically every EMA and EMI data we want to gather. The core of this data structure is a complex nested tree-like element construct with nodes and leaves on the tree, where the leaves can be outputs or inputs, depending on which inputs can be, for example, multiple choice, single choice questions, date picker, and so on. Also, text elements can appear in each leaf element in the tree. For example, simple text, but also complex text elements with placeholders for dependencies, for example, to other elements where user inputs are given or external sources. The most important part of this data model is that each and every single element in the questionnaire element tree can have a condition which can depend on one or multiple in complex nested tree-like condition structures on user inputs or also in external sources to omit and include some parts of the tree-like structure in the questionnaire. Last but not least, answers are stored in the answer sheets. Yeah, basically the whole framework is realized in the programming language Dart with the Flutter cross-platform framework. In the past, we mainly or exclusively developed in natively with Swift and Java for iOS and Android systems. So it was a huge step away for us from that accustomed native approach to a newer, more modern cross-platform framework approach, which also comes with its up and downsides, of course. One component of this to mention is the block pattern, the business logic component pattern, which is very well established in the Flutter community and Flutter ecosystem. Also, we therefore built all components of the framework with this pattern. For example, the EMA questionnaires are realized as nested tree-like structures consisting of block components which communicate via data streams with each other. In more detail, here the questionnaire is represented by a form block which is responsible for reacting to user inputs like next page, previous page, exit questionnaire, or submit the questionnaire. Also, this component listens to the current page block. The said current page block is responsible for the progress bar and the skip to the next question button, for example, and also listens on the current answer sheets block. Each and every element in this questionnaire tree has its own block component, which is responsible for the UI inputs for this element, but also sends those UI inputs to the answer sheet block, which in turn publishes them on the streams for the other elements to react and adapt to that new user input. Therefore, for example, if a condition anywhere in the element tree says if user input XYZ is given, then, for example, omit a whole tree branch and do not show it in the questionnaire. Last but not least, all answers are, user inputs are stored in the current local answer sheets block. So, to put everything together, I will briefly introduce you the field of application and then present the app itself. The first field of application for our framework was a large-scale German study on breast cancer aftercare called the Better Care Project. In this German project, multiple clinics and institutions are involved at several parts of the project, so I will only focus on those aspects relevant for our framework. The background here is that in Germany, the primary treatment for patients with breast cancer is at a very high structural process and treatment standard. However, currently, concepts can be improved regarding the implementation of evidence-based, individualized aftercare for patients with breast cancer after the primary treatment ends. Therefore, the primary goal of the study is that to investigate the increase in the overall health-related quality of life of patients included in the Better Care program versus those not included with usual care programs. Also, a secondary aim is to establish a multidisciplinary care network and to establish individualized aftercare for those patients. Therefore, a cluster randomized trial is set up with each 15 centers with intervention and control groups, 15 each, with a total of 1,140 cases.
I guarantee you.
Once elevated distress is identified.
Some example.
Excuse me? Should I interrupt or?
I don't know what happened. I guess it is in the WebEx. Okay, you continue.
Okay. So, once elevated distress is noticed in the patients after completion of primary care, those patients are offered a psychological intervention called Act on Cancer. Therefore, our framework was utilized for a just-in-time adaptive intervention mobile application for adult patients with breast cancer after the primary care ends. The ACT in the name stands for Acceptance and Commitment Therapy. So now I will give you a quick journey through the mobile application resulting from the framework and generated by the framework. So after the loading screen, users are presented the login page as far as they are not already logged in, and from there they are delegated to the main menu screen with the home screen, where also news and any information relevant for the patient is given. The most common use case scenario is that a notification pops up on the smartphone of the patient. Then they are led to the, for example, EMA diary questionnaire, and then they fill this out. On the right side, you can hopefully see that depending on the answers given in the questionnaire, the following elements change accordingly. That's element 3 I talked earlier about. So after submitting the questionnaire, the users are prompted an intervention option pane where they can choose from accordingly to the questions they have given previously in the submitted questionnaire. So one specialty of our of the interventions are checkpoints. Those in combination with the just-in-time EMA data and the customization abilities and adaptabilities of the framework build the core of the intervention component here. Also, the patients and contents of the mobile applications are managed with the eZeno platform, which is developed by the Department for Clinical Psychology and Psychiatry at the Ulm University in close cooperation with us. And as part of the Better Care project, the eCoach and CMS web applications as well as the patient web application are utilized in the project. The content management system and the eCoach platform generate the application data, and this data and the patient application features are also integrated in the mobile app on the phone. And this mobile app is used as described in the Better Care project. So, to sum it all up, we created a highly configurable, back-end independent mobile application framework for application in studies containing EMA, ecological momentary assessments, ecological momentary interventions, and even just-in-time adaptive interventions. So, our next steps will be improving the core code base and enhancing it with new features like, for example, statistics, to show the user its own progress, gamification, sensors, and so on. Also, 2 new projects are right around the corner, mid-2023 and early next year. So, I hope you enjoyed my presentation, and I'm looking forward to answer all the questions either now or during the rest of the conference. Thank you for having me today.
The technical problem is caused by the microphones. We hear your voice in reinforcement, but you cannot do anything about the
Okay.
question.
I didn't notice anything till the speaker turned up.
Questions? Yeah.
Thank you for the presentation. Very impressive architecture.
Thank you.
Is this app in the end for my glimpse? It sounds like it's rather general purpose app with all these use cases. And are there some parts that are really tailored for breast cancer? Because, like, for example, the questions sound like I can also use them for other studies, for example.
Okay, a very good question. Basically, it's general purpose, and each questionnaire can completely configured free of any field of application. So in the past, we developed, for example, for the Unity project and other tinnitus projects. Also, we have stress apps or for pregnant women and so on, and like 24 different use cases, and each of that use case and many more can be represented and configured with that application. So to put it in a nutshell, yes, you basically can put every questionnaire into that system. And yes, I think that answers the question. Okay.
Final questions? Yeah, of course, there was a question.
Okay.
Yeah, then I will ask this question. There's a classic one. EMR demands some sort of self-discipline from the person. Is it possible to incorporate in this architecture some kind of, don't know,
The gamification, for example.
I don't know whether it is a gamification,
Okay.
but some mechanisms that allow the clinician to monitor adherence and to intervene or something.
Okay. Currently, everything the user puts in that application can be monitored with the eCoach platform. The eCoach platform itself is not part of this mobile application framework, but is behind that interface adapter for the backend. So if the backend supports monitoring, of course, and you also are able to intervene, we got a chat-like function, but it's not fully tested yet. It's still under development, but technically it's possible, but not yet deployed in any project. And if I remember correctly, the Isano platform itself, which we use to generate the questionnaire content, this platform has such features you just mentioned, and I'm sure that in the next few months those features are also find their way in our framework for the mobile app.
Okay.
Yeah.
Hello. I cannot hear you.
Currently not.
Okay, so thank you very much. Last talk is feedback video.
Okay.
And
That is the
say that again?
from the online.
Yeah, are they online?
Yeah.
Okay, so it's
What was this? This wasn't the only thing. It's the generic for the dance.
Posso interagire da qua o posso andare? No, anche da qua, però non vedo più la condivisione, perché? Perché stava condividendo lui. Aspetta, lo faccio da qua. Sì, sì.
I wonder whether the keynote has been removed here. Carson said something about gamification. Now, then again, a blood flow game.
Yeah. Do you know where is located the video?
Hello everyone, my name is Elton. I am one of the authors of this paper, and we're going to discuss a serious game based on blood flow concepts and smooth particle hydrodynamics. Let's go. We're going to fulfill this agenda. We have some introduction, and then we present our fundamental concepts. We're going to present our methodology. Then we show our results and discussion, and then finally we have our conclusions. Well, a serious game is a combination of several concepts involving educational competence, a serious purpose, game techniques, and some fun and storytelling in order to create a game to help it to, for example, to teach some boring task or some complex matter, or in other words, we try to make more fun a pedagogical activity. In our lab, we work with numerical simulation of blood flow inside of blood vessels. And you use a technique named smooth particle hydrodynamics to solve the numerical equations that modeling the blood flow. And this is a sample of our simulation made in our research group. And we use this simulation to create a serious game based on the concepts of angioplasty and catheterization. The game was developed in a 3D environment in a Unity IDE, and the main object is to assist learn healthcare students. Let's talk about smooth particle hydrodynamics. It's a method to approximate or to solve differential equations. And the idea is to approximate a certain value of a property, any property that we name A, in terms of the property in its neighboring particles. Then we have a great set of particles that represent a fluid, and we approximate the physical properties of this fluid, like velocity, position, acceleration, viscosity, pressure, among the others. Then we solve these differential equations, and you have a good simulation of the fluid, in particular, in your case, of blood flow. This is an overview of SPG method, and we first evaluate the nearest neighbors of the particles. We estimate the value of pressures in each particle. Then we add some forces in this overview: gravity, compression resistance, viscosity. In a blood simulation, we have the pulsatile force, and finally we do a temporal integration to update the velocity and to update the position of each particle in each time step. This is a pretty good technique, and you have good results in the simulation. Here are a set of parameters that you use in your simulation, some idea of radius of each particle, reference density of blood, viscosity, the gravity, neighbors per particle, and so on. Gamification. The predominant scene of our game is a 3D model in a blood vessel. The blood circulates through the vessel, and the player is encouraged to move a stent through the vessel and position in the right region to reduce the obstruction. The Unity game engine was chosen. C# was the main language program. To complete the game was performed in 4 stages, At the beginning of each stage, a panel with necessary instructions is presented to the user in order that he knows what to do and how to proceed. To the game evaluation, you use a questionnaire based on technology acceptance models, and a group of graduate and postgraduate students in the health area. We had 13 volunteers to evaluate our game. And the questions were divided in two parts. The first one were focused in the user. We want to know the age group, the level of education, and if they have ever used graphic environments. And the second was directed to the game. We want to know the perception of the target audience, if there was any difficulty in the gameplay, if these simulations would help in understanding the concepts given in an eventual classroom, in their opinion. In the first opening scene of our game, we have a heart. This is an animation, the heart is moving, and this is a first scene that the user is going to see. After that, we have a panel with instructions in order to give directions to the user how to proceed or how to play the game. The first stage, we consider the easier stage to be performed. The player will have 3 chances or 3 lives to reach the end of the game. And the first one consists in taking the stent to the arteroma plate and opening without going through the bifurcations in the blood vessel. The navigation is done through the keyboard arrows, and if successful, the player moves to the next phase and a hit is counted. Otherwise, the player loses a life and the stage is returned to its initial position. It's a print screen of the first stage. Here's an initial blood begin to flow to this vessel, and here is the arterial plate, and here is the stage that the user have to move in the right position. The second stage is a little more difficult. The arterial plate is changing its position and is more difficult to reach than the first stage. At the third stage, there was several questions involving the circulatory system, and the user has to give the correct answers in order to count or reach to his performance. Then this answers was randomly chosen in your data bank. And is altered to different users. The last stage is considered the more difficult due to the shape of the blood vessel, which has 4 bifurcations, and we have 2 auxiliary views in order to use to help the user to navigate in this blood vessel. In the game evaluation, we have 13 answers in our volunteers, and we have that most of them is progressing is Master PhD. And in the age range, most of our users, most of our players are between 21 and 30 years. Just 2 of them a little older and just 2 a little younger. So in this evaluation, we ask about the easy to use perception and familiar with graphical system. And we noticed that the familiarity with graphical system has little influence in the user perception. Even users with little familiarity with graphical system have a high score to the easy to use perception, which is good. The next evaluation, we analyze the easy of use perception versus the range of age of users. We suppose that older the user, less easy to use perception to them. But the results were very inconclusive. Then we have most of our users is at this age range between 21 and 30, and we have a lot of different answers to this, a lot of different scores to this question. So we have no final conclusion about this answer. And the next evaluation was to analyze the intent to use versus familiar with graphical systems. And we noticed that we have a high score in the intent to use, which is very good. And the familiarity with graphical system has little influence on the intent to use, which is a grateful surprise for us. Finally, the intent to use versus educational level. We notice here that 2 graduated students has no intent to use a game in educational context, which is comprehensible because they have no perspective to work with educational issues at this point of their career. So it's pretty understandable. The users contribute with several suggestions to improve our game. Among them, we can list leave the instructions on the screen a little longer, work on more on the flow variables like pressure, radius, viscosity, and so on. Display a final report with correct answers to the questions, including more questions and more challenges with the stent, as well as pharmacology and cardiovascular system. Set a time visible to player, both to perform tasks and to answer the questions, which is a very good suggestion. And add background music with the option to disable on the player demand, which is pretty good question, pretty good suggestions. And our conclusions is that we develop a prototype of a game based on computational fluid dynamics and blood flow concepts, which has great room to improvements. And the objective was to introduce a playful and a fun way concepts related to the circulatory system. The analysis made points of interest and show potential of user gaming pedagogical context. The project is still in development and it's possible to produce variations and test new features. And we intend to refine the elements of the game with more refined graphical interfaces, new phases, and new challenges. We also intend to implement a data collection which includes detailed descriptions of player errors and corrections, as well as responsible times. Well, thank you everyone. I hope you enjoy our presentation and we are happy to answer any question that you have. Thanks again, everyone.